ke ruangan video conference Ceramik Teknologi Webinar. Bismillahirrahmanirrahim. Alhamdulillahirrabbilalamin. Wassalatu wassalamu ala ashrafil anbiya'i wal mursalin wa ala alihi wa sahbihi ajma'in. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera dan salam pembuka bicara. Yang berbahagia, Profesor SRIR Dr. Suhaimi bin Abdul Talib, merangkap penolong naib Chancellor Kolej Pengajian Kejuruteraan UiTM. Yang berbahagia, Profesor Dr. Nur Hamidin bin Muhammad, selaku Presiden Malaysian Powder Metallurgy and Particulate Materials Association. Yang dihormati Encik Rahimi bin El Muhammad selaku Pengarah Urusan Maju Saintifik Sendirian Berhad dan RS Advanced Technology Sendirian Berhad. Yang dialu-alukan Profesor IR Dr. Abu Bakar bin Sulong daripada Universiti Kebangsaan Malaysia, Profesor Madya Nuraini binti Wahab daripada Universiti Teknologi Mara, Encik Abdul Rahim bin Muhammad Sahab daripada Sirim Berhad, Puan Marziah binti Cik Murad daripada UiTM dan Profesor Madya Dr. Muhammad Hussein bin Ismail daripada UiTM. Juga tidak ketinggalan diucapkan selamat datang tekan jaringan industri, komuniti dan alumni Profesor Nur Razak serta semua hadirin warga maya yang dikasihi sekalian. Selamat datang sekali lagi diucapkan ke Ceramik Teknologi Webinar. Saya Nur Marsyana Suha binti Muhammad Sadura bersama-sama Nur Izian Syamimi binti Razali dan Asila binti Muhammad Jamal selaku pengacara majlis anda pada pagi ini. Bagi memberkati majlis kita pada pagi ini, dijemput saudara Muhammad Haris Imran untuk memimpin bacaan doa. Majlis dengan segala hormatnya mempersilakan.
Terima kasih kepada pengurusi majlis. Kita mulakan dengan umum kitab Al-Fatihah. Alhamdulillah. A'udzubillahi minasyaitonir rajim. Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin wassalatu wassalamu sayyidina Muhammadin wa ala alihi washabbihi ajma'in. Ya Karim, ya Wadud, sesungguhnya kami berhimpun pada hari ini bagi menyatakan kesyukuran di atas kurniaan-Mu yang tidak ternilai. Jadikanlah kami hamba-hamba-Mu sentiasa bersyukur sama ada nikmat yang sedikit, lebih-lebih lagi nikmat yang limpah ruah kepada kami. Ya Allah, ya Rahman, ya Rahim, Engkau berkatilah dan rahmatilah perjalanan program Ceramik Teknologi Webinar pada hari ini. Sesungguhnya Engkau Maha mengetahui bahawa kami di sini ingin menimba ilmu-Mu yang sangat luas bagi mengembangkan ilmu pengetahuan kami sebagai hamba-Mu yang Engkau radai. Seteru berkatilah dan rahmatilah perkebunan kami ini. Kurniakanlah kepada kami ilmu-Mu. Sinarilah hati-hati kami dengan cahaya dan hidayah-Mu. Semoga dengannya kami mudah menerima dan menghayati serta mengamalkannya. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina azabannar. Wa sallallahu ala sayyidina Muhammad wa ala alihi washabihi wasallam. Walhamdulillahi rabbil alamin. Amin ya rabbal alamin.
Amin, amin, amin ya rabbal alamin. Terima kasih diucapkan kepada saudara Haris atas kesudian mengetuai bacaan doa sebentar tadi. Emas tempawan buatmu puteri, busana indah buat rupawan. Sudilah tuan tampilkan diri bersama madah kata alu-aluan. Dengan segala hormatnya, majlis ini menjemput Profesor SRIR Dr. Suhaimi Abdul Talib selaku penolong naib Chancellor Kolej Pengajian Kejuruteraan UiTM untuk menyampaikan ucapan alu-aluan. Majlis dengan segala hormatnya mempersilakan.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Terima kasih saudari pengacara majlis. Yang saya hormati rakan yang lama tak berjumpa, Prof. Dr. Nur Hamidi Muhammad selaku Presiden Malaysian Powder Metallurgy and Particulate Materials Association. Yang saya hormati Encik Rahimi El Mahmud, Managing Director RS Advanced Technology Sdn Bhd dan Maju Scientific Sdn Bhd. Terima kasih Cik Rahimi di atas kerjasama dan persahabatan yang terjalin di antara syarikat dan juga pengajian jururawat mekanikal. I think we have gone a long way back with this company. Prof Engineer Dr. Abu Bakar Sulong, Prof Abu, mungkin belum terlewat bagi saya untuk mengucapkan tahniah di atas terpilih oleh Akademi Sains Malaysia sebagai top research scientist di Malaysia, ya. Tahniah, and we thank you very much for your presence here to share your expertise and experience. Encik Rahim daripada Sirim, terima kasih berada bersama-sama dengan kita untuk berkongsi pengalaman. Prof Madya, Dr. Nuraini Wahab, pensyarah daripada pengajian kejuruteraan mekanikal. Puan Marziah juga daripada pengajian kejuruteraan mekanikal. Puan Marziah, kita doakan sama-sama, ya. Semua yang ada dalam majlis ni, saya minta kita doakan agar Puan Marziah menghadapi viva dia. Dan the next time kita jumpa dia, kita akan panggil dia bukan Puan Marziah, kita akan panggil dia Dr. Marziah. InsyaAllah, kita doakan supaya dipermudahkan sesi viva beliau. Dan juga kepada Dr. Hussein yang yang memang kata Prof Medi tadi memang orang kuat lah. Dr. Hussein, kita doakan diberikan kesihatan, kekuatan dan terus untuk berkhidmat dalam bidang kejuruteraan ini, ya. Dan tidak dilupakan rakan saya, Dekan Jaringan Industri untuk Kolej Pengajian Kejuruteraan, Prof Nur Azhar Abdul Rahman, dan juga peserta-peserta Ceramic Technology webinar ini. Saya berterima kasih kepada pihak penganjur kerana sudi menjemput saya untuk memberikan sepatah dua kata. Seminar ini merupakan penganjuran kerjasama di antara pihak syarikat RS Advanced Technology Sdn Bhd dan Maju Scientific Sdn Bhd, dan juga dengan rakan-rakan daripada UKM, daripada Sirim, dan bersama dengan Kolej Pengajian Kejuruteraan. This is a very specific area, yes. Ceramic is a very specific area. It is not only in terms of the coming up with the composition, but also we need to look at the processes and also the new uses of ceramic dalam dunia kita yang sedang berubah. And these are the areas, apa orang kata, bila ada area-area baru ni, pada peserta-peserta, terukailah bidang-bidang baru ini, sebab bidang-bidang baru inilah yang akan, apa orang kata, this will define who you are. Sebab kalau kita buat bidang-bidang yang, apa orang kata, bidang-bidang yang orang lain sudah buat, bidang-bidang yang telah banyak dah di-establish, then you can look forward to be one of the rest. But if you focus on these new areas, these emerging areas yang baru, mencari kegunaan dalam bidang-bidang yang baru, then there is a highly possible that you will be one of the best. So jadi bagi saya, sesi ini perlu diambil, apa orang kata, manfaat yang sepenuhnya oleh peserta. Dapatkan ilmu. Ilmu itu daripada industri. Cik Rahimi ada dengan kita in the topmost, the frontiers of research. Saya rasa Prof Abu berada di situ, ya. In terms of the apa orang kata, things yang related to regulation ke apa, mungkin boleh bertanya dengan saudara kita daripada Sirim tadi, Cik Rahim, we should be able to put together. So in terms of knowledge, and also this is a very apa orang kata, niche area. This is a very niche area in mechanical engineering and materials engineering lah. Saya rasakan kehadiran peserta yang ada lebih kurang dalam 60 orang ni, mungkin tolak penceramah dan urus dia, there is 50 of you. This is a good opportunity for you to establish networking. Networking amongst you yang sebaya, because you are going to grow up together in this field of industry, in this field of research. So jadi ambillah peluang ini sebaik-baiknya, dan saya sebagai seorang yang telah melalui perjalanan ini daripada mencari bidang, membuat bidang, to excel in the bidang sehinggalah menjadi penilai dan sebagainya. I think you need to stay focused dan tidak berputus asa. This is the traits that we need dalam normal baru ini. You need to be able to be flexible, to be able to adapt to the situation, and you must be able to look into the future, scenario planning dan juga foresight analysis to see what are the areas yang boleh berkembang. Dan untuk ini, you need a little bit of hand holding, maka gunakanlah apa orang kata your seniors yang ada di dalam industri, di tempat kerja ataupun di universiti tempat belajar. Mereka ini sanggup dan sedia membimbing. Setakat ini sahaja saya punya kata-kata aluan. Kalau tak disetkan dalam telefon saya tu untuk dia berbunyi supaya saya berhenti, saya takut nanti saya bercakap lebih daripada apa yang kita punya pengacara majlis izinkan. Jadi saya dengan ini mendoakan agar seminar webinar ini berjalan dengan lancar dan segala usaha perancangan, pelaksanaan dan post webinar ini diberkati oleh Allah SWT. Sekian, wabillahi taufik. Wassalamualaikum warahmatullahi wabarakatuh.
Majlis merakamkan ucapan ribuan terima kasih kepada Profesor SRIR Dr. Suhaimi Abdul Talib di atas ucapan alu-aluan itu tadi. Majlis diteruskan lagi dengan ucapan daripada Profesor Dr. Nur Hamidi Muhammad selaku Presiden Malaysian Powder Metallurgy and Particulate Materials Association MPM2A. Oleh itu dengan segala hormatnya dipersilakan.
Ya, bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Terima kasih fungsi majlis Prof Dr. Suhaimi Abdul Talib. Rakan lama tak jumpa, baru jumpa ini penolong Naib Chancellor Kolej Pengajian Kejuruteraan UiTM, Prof Nazah, Timbalan Dekan Kolej Kejuruteraan UiTM, sahabat baik saya lah, PM Dr. Husin, dia orang kuat society lah, dan juga jawatankuasa penganjur seminar, rakan-rakan pembentang Kertas Kerja, 6 orang tu semuanya muka-muka lama, ada juga yang muka baru, dan juga semua peserta Ceramic Teknologi Webinar. Pertama, marilah kita mengucapkan syukur kepada Allah SWT atas limpah kurnianya kita dapat bersama-sama dalam webinar ini. Walaupun secara dalam keadaan normal baru, dalam secara maya, kita berharap kita dapat berjumpa face to face, tapi insyaAllah kita doakanlah agar pandemik ni boleh berakhir dan kita akan dapat organize semula aktiviti-aktiviti kita ni secara face to face seperti sedia kala. Saya bagi pihak Malaysian Powder Metallurgy dan Particulate Material Association ataupun MPM2A ingin mengucapkan tahniah kepada pihak penganjur iaitu Dr. Husin dan rakan-rakan serta syarikat PS Teknologi, Raimi. Memang Raimi ni dia selalu datang UKM tapi saya tak pernah berkesempatan untuk jumpa. Raimi dan juga of course atas inisiatif untuk menganjurkan webinar ni, dan saya juga ingin mengucapkan terima kasih kepada pengurusan Kolej Kejuruteraan UiTM lah yang memberi sokongan untuk memastikan program ini dapat dilaksanakan. Saya juga ingin mengucapkan ribuan terima kasih kepada semua peserta yang dapat hadir pada webinar ni. Saya rasa gembira lah dan teruja melihat ramai muka-muka baru yang dapat hadir dalam webinar ni, yang tak pernah kita jumpa dalam seminar-seminar yang pernah kita adakan sebelum ni. Dan kita harap yang muka-muka baru ni akan dapat meneruskan pendidikan yang dalam bidang yang kita perlu lakukan dan sebagainya. Dan alhamdulillah lah hari ini kita bertuah kerana bersama-sama kita ada 6 orang pembentang yang hebat-hebat, ramai daripada rakan-rakan saya yang datangnya daripada pihak industri, institut pendidikan dan universiti yang sudi berkongsi ilmu dalam bidang seramik dalam pelbagai aspek. Kalau kita tengok macam Prof. Suhaimi sebut tu, kalau dalam pembentangan hari ni kita tengok mereka panel-panel pembentang kita ni menyentuh daripada asas bahan seramik, kaedah pemprosesan yang menggunakan pelbagai teknik, penggunaan bahan seramik dalam industri dan juga mungkin perkongsian pengalaman kerjasama antara industri dan juga universiti, yang mana saya tahu Dr. Hussein dan rakan-rakannya banyak bergerak ke arah ini. Saya yakin banyak yang kita dapat belajar dari pembentangan mereka nanti, insyaAllah. Dan kalau kita tengok secara keseluruhannya masih banyak ruang yang boleh kita terokai dalam bidang seramik ni. Antara kajian dalam bidang seramik, contohnya antaranya dalam bidang seramik termaju, contohnya penggunaan dalam bidang bukan konvensional ataupun teknik dan kaedah pemprosesan terkini menggunakan additive manufacturing dan sebagainya. Jadi saya selaku ketua panel Grant Pendidikan dan Aktiviti dalam bidang teknologi kejuruteraan ni, kita dapat tengok over the years peningkatan permohonan grant pendidikan dalam bidang ni, bidang seramik menggunakan seramik termaju, kaedah pemprosesan termaju. Cuma isu yang kita harus lihat bila dalam mengukakan permohonan pihak kementerian ni, kerana kementerian ni kita tahu grant-grant dia ada tema-tema yang perlu kita ikut. Kalau dia kebanyak, the bigger chunk of grant kita ni dalam bidang fundamental research. Jadi kita kena pandai mengolah proposal kita tu. Bila kita mohon pada dalam grant FRGS, kita kena pastikanlah permohonan kita tu berbentuk fundamental. Memang agak sukar bila kita mohon kalau contohnya untuk menggunakan kaedah ataupun nak melihat dari segi aplikasi advanced ceramic dalam bidang baru, kita tend to write proposal kita tu dalam bentuk applied. Jadi panel ni boleh tengok nampak applied sikit dia, reject terus lah. Kan? The buzzword yang dekat panel ni, ada few dalam ni panel-panel yang pihak kementerian, the buzzword is reject. Tapi pada masa yang sama saya ingin mengucapkan tahniah lagi lah pada UiTM kerana mendapat kelulusan yang agak besar dalam penilaian FRGS yang lepas. Tahniah saya ucapkan. Cuma tak boleh beat UKM lah kot dari segi percentage of success. Itu saja nak naikkan UKM sikit. Okey, tuan-tuan dan perempuan sekalian, saya tak nak ambil masa lama, jadi selalunya pengacara yang puncak yang kedua ni dia tak boleh lebih daripada puncak yang pertama. Dan nanti dia lawan tuan lah. Jadi saya hanya ambil sikit-sikit peluang ni sebagai Presiden Malaysian Powder Society untuk menerangkan sedikit tentang persatuan ni. Secara ringkas persatuan ni ditubuhkan pada tahun 2009 dalam seminar antarabangsa yang kita tubuhkan semasa tu, yang kita anjurkan, dan semasa tu kita ada beberapa guest speakers daripada overseas yang datang bagi talk and so on. Antaranya yang prominent researcher dalam bidang ni, Prof. Miura masa tu. Dan alhamdulillah kita dah dapat tubuhkan persatuan ni, dan tujuan utama persatuan ni ialah untuk mempromosi dan menggalakkan pendidikan dan pembangunan serta pengkomersialan dalam bidang powder metallurgy dan particulate material di Malaysia. Jadi pada yang belum jadi ahli dan minat jadi ahli, saya mengalu-alukan saudara-saudari sekalian untuk mendaftar jadi ahli. Orang kuat persatuan ada di UiTM, kita ada Dr. Hussein, kita ada Dr. Hafiz, kita ada kalau di UKM, kita ada Prof. Abu, dan Prof. Raimi, Dr. Raimi sendiri, Cik Raimi sendiri pun merupakan rakan industri dalam persatuan ni yang banyak menyumbang dan menyokong persatuan. Yurannya pun murah Yurannya murah, saya ingat, saya ingat tak lupa, RM20 je kot. RM20 untuk seumur hidup. Bayar sekali je. Sebab tujuan kita bukan kita untuk menjana pendapatan daripada yuran keahlian, kita nak dapatkan ramai yang terlibat dalam persatuan ni. Kita ada aktiviti lain untuk menyumbang pada tabung persatuan, insyaAllah. Dan salah satu event yang selalu persatuan adakan ialah persidangan tahunan, yang mana kita berusaha untuk mengumpulkan semua players dalam dan dari pihak industri dan juga akademia dalam bidang ni untuk duduk bersama berkongsi pengetahuan dan dapatan klinik antara satu sama lain. Selalunya kita akan adakan seminar ni secara dalam internet, secara nasional, peringkat nasional dan peringkat antarabangsa alternately. Selalunya setahun kita buat secara dalam peringkat nasional dan tahun depan kita akan buat peringkat nasional. Dan kita berharap pandemik ni dapat berakhir sebab kita merancang untuk mengadakan seminar ni lagi. Dan kalau kita haraplah seminar pandemik ni dapat berakhir dan juga proses travelling ni dapat dipermudahkan, dan kita kalau semuanya berakhir, kita harap kita dapat mengadakan seminar ni sekali lagi tahun depan. Seperti yang saya sebut dalam seminar semasa yang kita buat di UTP itu, kita dah bincang dalaman dan kita minta Prof. Abu dan juga Dr. Husin jadi key players untuk menggerakkan seminar. Kalau tak dapat peringkat antarabangsa, mungkin kita buat peringkat nasional dulu. Kita harap kita dapat laksanakan tahun depan, insyaAllah. Sebab saya rasa dah 3 tahun since the last seminar yang kita buat. Sebelum kita jangkakan kita nak buat sebelum tu, sepatutnya Dr. Husin yang take over kan, Dr. Husin, selepas yang kita buat di UKM. Tetapi oleh kerana pandemik, kita terpaksa batalkan dan insyaAllah kita harap kita dapat laksanakan, insyaAllah. Jadi akhir sekali, saya sekali lagi ingin mengucapkan tahniah kepada semua yang hadir dalam webinar ni. Tahniah dan terima kasih kepada Urustia, dan setinggi-tinggi terima kasih kepada rakan-rakan pembentang yang hebat-hebat semua ni kerana sudi berkongsi ilmu dengan kita semua, insyaAllah. Akhir sekali saya ucapkan terima kasih kepada semua dan saya sudahi dengan wabillahi taufiq wa hidayah. Wassalamualaikum warahmatullahi wabarakatuh.
Majlis merakamkan jutaan terima kasih kepada Profesor Dr. Nur Hamidi Muhammad di atas ucapan sebentar tadi. Majlis diteruskan lagi dengan sesi bergambar bersama VIP sebelum Profesor SRIR Dr. Suhaimi Abdul Talib mengundurkan diri di atas urusan yang tidak dapat dielakkan. Hadirin sekalian diminta untuk membuka kamera dan bersedia untuk sesi bergambar.
Ya. Kak. Semua diminta bersedia. 1, 2, 3. 1, 2, 3. Sekali lagi. 1, 2, 3.
Terima kasih kepada semua yang memberi kerjasama.
Okey, rakan-rakan, saya mohon minta diri ya. Mudah-mudahan berjalan lancar lah. InsyaAllah kalau pandemik ni dah berakhir dan kali kita ada majlis, kita berjumpa secara semuka. Okey, Assalamualaikum.
Terima kasih Prof.
Terima kasih Prof.
Saya pun ingin mohon undur diri. All the best dalam presentation nanti. Okay. Assalamualaikum.
Terima kasih Prof.
Salam.
Terima kasih Prof.
Tanpa melengahkan masa, majlis diteruskan dengan perkongsian daripada panel jemputan pertama iaitu Encik Rahimi bin L. Muhammad selaku pengarah urusan Maju Saintifik Sdn Bhd dan RS Advanced Technology Sdn Bhd. Beliau berpengalaman bertugas di SIRIM dalam penyelidikan berkait dengan advanced ceramic, composites dan fabrication processes selain daripada pernah bekerjasama luar negara seperti Korea Batech Corporation, Shimbo Technical Research dan American Isostatic Presses. Dalam pada itu, beliau juga telah berjaya mencapai beberapa pencapaian di SIRIM seperti ceramic grinding ball, silicon matrix composite dan ceramic injection molding. Dengan segala hormatnya, majlis mempersilakan Encik Rahimi L. bin L. Muhammad untuk menyampaikan perkongsiannya yang bertajuk Oxide Ceramics Manufacturing Components. Majlis dengan ini mempersilakan.
Okay. Bismillahirrahmanirrahim. Alhamdulillah Rabbil Alamin wassalatu wassalamu ala asyrafil anbiya'i wal mursalin wa ala alihi washabihi ajma'in. Assalamualaikum, salam sejahtera and a very good morning to all. Thank you, Mr. Chairman and Moderator, Cik Asila Jamal. I would like to take this opportunity to thank our special guest for this webinar, Professor SRIR, Dr. Hadi Saimi Abu Talib, Assistant Vice Chancellor, College of Engineering, UITM, and Prof. Dr. Nurhadi Muhammad, President, Malaysia Powder Metallurgy and Powder Material Association, and BM2A, the short name. And congratulations to Prof. Dr. Nurhadi also, because he was promoted to Pro NAP Chancellor, Penjanaan and Prasarana UKM recently. So Tanya. Okay, a very special thanks and warm welcome to speakers, all speakers, and also thank you for the committee, organizing committee, for making this webinar into reality, especially UITM under Dr. Muhammad Hussein. Okay, and I would like to welcome all the participants, Dr. Dating, Prof, so many Prof here, and Prof Madya, Dr, Miss, Madam, Mr, and all students. So it's very nice to meet all of you. So let me please allow my proceed with my slide. Okay. I share the slide. The screen. Okay. Is it okay? See? Boleh nampak ke? Sorry.
Belum.
Belum lagi. Kejap ya. Pasal ya, saya tengah ni.
Nampak slide.
Okay, your entire screen. Okay, kejap. Share. Okay. I think share already, right? Nampak? Belum lagi.
Belum Mr. Rahim.
Belum. Come share nanti. Kenapa tak boleh? Saya share sekali lagi. Window. Okay, Oxide Ceramic, share. This one okay?
Dah mula nak masuk. Okay.
Okay, boleh? Okay. Okay, so saya kena buat satu-satu lah. Dia tak boleh nak ni lah. Okay. Boleh nampak? Tak masalah.
Boleh.
Okay, my topic today is Oxide Ceramics Manufacturing Components. So I have two company, Margin Scientific Sdn Bhd and RS Advanced Technology Sdn Bhd. Okay, this is my basic lah. Ni yang kata short brief history lah. So you have my phone number here, you have my email here, and you can contact me anytime. So actually from from 1986, I just go out from Kelantan to study to MSN Perlis and then MSN Kuantan, and then finish my study in WMU, this Western Michigan University, USA. So in Bachelor Science of Engineering, Mechanical. And then coming back to work with Sirim Berhad in 1992. This is CTC means for Ceramic Technology Center, and this is the me. Okay, this is me with the machine, and this is the start of the history of the dealing with ceramic, and then know a lot of experience and learn about ceramic lah. Because in engineering, even in the US or in my study before, so we don't have any background on the ceramics. So when we when I work in Sirim, so we have some group of college, and then we work into advanced material and also conventional. So we gain a lot of experience from here. So this is for starting. And then Sirim Berhad go for corporation on in 1996. So that's why I left. Then so I not joined. So I joined the KGE. KGE is stand for Quantum Electromart. This is a trading company. So from here, I learned about business, how to do some business, how to dealing with customer, and some finance. So how to manage the company. So of course, this is very important lah for me. And then, of course, during 1998, there is economic turmoil, something wrong with the US dollars at that time. So economy downtown. So the US dollar become in ringgit Malaysia become undervalued. So it's double that time. So KG decided not to going to move on. So I tried to save the trading company. So during that time, it's 1998. So I established Maju Centurion Berhad. This is mainly for supplying equipment and do the consultancy, because we have already existing customer like Sirim and university. So I cannot just left like that. So we try to do whatever we can. And then after 2 years, I established as advanced terrorism Berhad. So with the money that again, so we try to establish one company that dealing with manufacturing. Of course, we can sell equipment, everything, but to deal with manufacturing is different thing. So I need to have some model of business manufacturing to see what is the main inside supplying parts and dealing with a big company industry like Proton. So very big company, but we are very small. But we dealing with them is a different story. So we gain a lot of experience. Okay. And here we have from my work before, so we can manage to buy the facility in Mutiara Subang. So luckily, so until now we have two facility. We have one in Mutiara Subang, Shah Alam. Mutiara Subang is in Subang Jaya, but Shah Alam is Batu Tiga is border. So in here, I believe some of you already visit. And here we do some trading, internship, visit, small seminars we do. We store the stock and the part. So we doing the small operation of Islamic Kaiping ground floor. So luckily we don't have to rent big place because it's quite small place. So we can produce the Islamic Kaiping. It's oxide ceramic, it's alumina. So in here we have facility. So we have ball mill, pressing, sintering, and CNC. So in here complete. So we can produce oxide ceramic in here. Slip castings we can do for oxide ceramic. So no problem. We can have start research in here also. So we also do some zirconia, whatever is involved in the oxide. Non-oxide is a different thing. So oxide ceramic you can do in the ground floor. Okay, in Kota Baru, we actually with the money that we keep, we can make stage by stage. So we continue making it bigger. So actually this is tanah persendirian lah, personal. And then so we try to do it step by stage. So now it's become big. I think if you want to rent here in Shah Alam, I think 20,000 ringgit I think per month. So we actually don't afford that to buy big facility in Subang Jaya, because ceramic is this is still new, and then we need to do some market and sell some of product, so continuously to get sales and then to overcome overhead. So this is a business scenario. So for us, so in here we can do follow research, which means that we can do first starting research in Shah Alam, and then we can follow up in the Kadok Kelantan. This is Kelantan, and then we can at the moment we are finished our research in filter, but not trying to make it production. It's a Rahas filter, and we try to do it production, because Rahas, of course, raw material machine is bigger, so we cannot do in double story facility. So we have to do in a very big place for this one. So you are all invited we try to make this place, Kelantan is a fun place, it's a playing place. You can play ceramic, you can do whatever you can do here, and you can make seminar. We call it a one-stop center to ceramic tourism. So people can come, and then you can play with the machine, play with the ceramics, and also there is homestay inside there, and there is around we have some homestay also and hotels, so we can do seminar around. So it's very nice to going back hometown and then we do some work. Okay, and this is some fun thing that we do in Kelantan. So it's a clay, porcelain, so we play with the color. So not only we doing the offset ceramic for advanced metal, but we try to vary our activities so that it become interesting. It's not just you doing engineering works, but of course other things also involved. Luckily in ceramics, when we're talking about ceramics, it covers all. It's chemicals and engineering and materials. So they are covered all the aspect of the technical areas. So that's why we have intern students so many wide areas from chemical, from engineering, mechanicals. Okay, so this is something that we try to develop in Kelantan. Okay, so we at the moment we have MOU with University UiTM, University Mara, here in 2019, and then just recently we have MOU with University of Science Malaysia. So we are developing for the nano silica. So we try to commercialize it. So we now checking in process of checking and try to make it production, and hopefully everything is in track. Okay. So this is our main activity today. So this slip casting. Slip casting, of course, maybe some of you know already. So we do both conventional and advanced material. Conventional, of course, everybody know that we can slip cast porcelain, clay, so some items that is related to decorations. But we also slip cast alumina, is advanced ceramic. But we didn't try the metal, but I don't think metal is not included for slip casting. But normally for ceramic, we use for alumina, zirconia for slip cast. This is the cheapest process for oxide ceramic. So if you want to do something, not really compacted, but you still want to see whether it's work, you can cast. So with the very low budget, this one you can make more from plaster mold and then casting. Of course, you need a furnace for that. Okay, and second is powder injection molding. So these are both we do metal injection and also ceramic injection. Of course, metal injection there is another company that we assist. But we doing a lot of work on ceramic injection. So I think ceramic injection molding, we have no problem. We already established the process, and we going to just waiting for orders for this one. So of course, it's not easy to do business. We need to do the marketing and then some connection or networking with the industry. We know some industry, but they already have. When talking about this business, we talk later about this. Okay, and then we have high vacuum and temperature hot press. So we don't have facility, but we supply this machine to some university. So I think it's very useful when you want to hot press, and HIP. HIP is the same thing as pressing in at elevated temperature, very high temperature. So you make a solid ceramics, oxide and non-oxide. So the very important thing we can do in RS Advanced is unit axial pressing and cold isotopic pressing. So this is a main machine, a main process that we can do and manufacture our component. So unit axial pressing, of course, deal with a lot of mold and die. It's a metal mold. Die is a tungsten carbide, and then cold isotopic pressing is a cheaper one. So you can use rubber mold. Whatever you go, and then you can carve or you can machine it. Okay, and then of course all the process you have to do some consolidation or vacuum sintering and surface sintering, and also peroxide is just normal air sintering. So you may find that the sintering is much cheaper than non-oxide. So this is that's why our company, so we stress on the oxide first, because for oxide, so it's easy to maintain the machine and to get the process done by using a process. So non-oxide is quite complicated. Okay. Other things that we do is machines, supply machines, services, repair, and etc. So supply materials, chemicals. So the last thing is we have hands-on training and manufacturing. This is what I mentioned before. We just mainly established as advanced and hard just to make model for us to get the idea how to supply to industry. Luckily, we involve industry, very big industry now. Very big. This is a Honda, a Proton, PHN. So Toyota is using our product now. So it's quite interesting dealing with this. You can go inside, no problem. You can see inside. You can deal with the workers, and you can discuss with the purchasing and the engineer what's happening there. So we know. This is why we're a small company, but it's like a small company staying outside from big company. So we are considered part of the big company, but we stay outside. So we are free. We can serve under the company. So that's the idea. So we have this is our machine. So we have automatic powder press, manual press, roller slip press, bench top lift. This lathe is a manual lathe before we have CNC. We talk about that later. Then Sigma mixer, we have powder injection molding, baking mixer, debinding, sintering furnace. This is for oxide. Okay, electric kiln, gas kiln, tube furnace, and then we have casting. Okay, finishing equipment. Okay, this is very direct and basic flow for compaction. Actually, apply to some of the process lah. So actually, we have raw. This for alumina. So we have binder and lubricant. So we just ball mill, and then mixing and ball mill and spray drying. So this is basic. So because of spray drying, you can fill into the mold so easily, and then the binder is used to bind all the ceramic all together. Okay, and then you can do the machining also in green body. So very nice. Machining is actually machining is very important for us because we can make blank, and during machining, I mentioned before why we need to explore more on machining, especially the CNC. So this is more than we need to explore anyway, because the trend is like that. So we cannot just pressing and then make the sintering. So this will involve what you call it software engineer. We call like AutoCAD. So many of our engineers. Yeah? So we hope that we can establish one unit for just doing the machining of the green body. And then of course sintering, and then sintered body. Sintered body very difficult for outside ceramic. When you sinter the ceramic, so maybe you can machine, but it's a micron feed, so it takes long time. So that's why we try to avoid after sinter. If that depends on the application. If the tolerance is okay, we show you what our product. So if the green body is okay, so we don't need the sinter body machining, so it's fine. So we can reduce the cost. So why we add cost without no need. I mean, no need to machining. So we save the money. So this is basic ceramics. We have conventional. We have advanced ceramic. Advanced ceramic, of course, oxide, non-oxide. So we have alumina. Advanced ceramic. We have zirconia. We have titanium oxide. So all this we do our own research. Of course, alumina and zirconia we do in Sirim before. That's why we know a lot. But after that, shaping and machining we do ourselves. We're using our facility. So it quite take longer time. And then of course I have to do something else. We have another business. So luckily we have intern student that attached, and of course they can learn and we can do it together. So this is very nice, because this is the things that you learn when you're doing research. You learn and something new, always new things coming up. So quite nice. Okay, conventional ceramic, of course, is a decorative item. Fuses, you can make porcelain for fuses, and this is very good business now and for porcelain because pandemic they use a lot of glove. So this is, I'm not sure here I can make it or not, but I don't think they are imported now, still imported, not localized. But I think the fuses is there is a company long time ago make the fuses, but I'm not sure they are continuing doing that. We would love to do it 40 MB, but the problem is, of course, we need to have time and then networking, and it's not easy because when you're dealing with the big customer like TMB, so when you jump into the business, you have to consistent. It's not like you go and then don't come back. Get out so easily. No. It's not. It's about the reputation. So when you're doing the business, so normally we do, and then we try to finish up our project, and then continuously supply with a good quality. So this is business, not just research. Business is different story. So it's something like we need to explore. So this is our what you call it, press before in Syrian. Also, this is our production now. We're doing this. This is cylinder, and this is piping. Okay, this is a press part. Okay, or ceramic, oxide ceramic. This is alumina, zirconia, and this is normally we do some exhibition. So we explain to customer or to some come here to see our product. So we explain to them what is ceramics. So very nice to share something that to people. Okay, this is a uniaxial. Of course, ceramic, oxide ceramic, non-oxide, and metal you can press uniaxially. Of course, this is uniaxial is very expensive. This polarization automatic, highly polarization. But if you order small quantity, it's not feasible for this one. But for high polarization, you supply monthly to the customer, so you can amortize your mold, and then you can, the machine can be, gain back the money. So this is we're looking for. Okay, so all the technology from simple to complicated, but this is polarization part. When we're talking about business, so we're looking for this. If you have very high polarization, high order, monthly order. Okay. So ceramic, oxide ceramic, we have two. So oxide ceramic, we have polycrystalline and we have glassy phase. So glassy phase is a glass. So sometimes you put some to make glass ceramic, some oxide crystalline to make glass ceramic. But polycrystalline is very important. Because ceramic is difficult to sinter if you have a bigger size of particle. Particle is one thing. Inside the particle there is a polycrystalline. You need to have very fine particle size to sinter it, densely. So we are talking about maybe 100 micron, submicron, 10 micron, 5 micron, submicron, nano size. So we have tried all that. So of course, nano size or submicron size is better to make strong ceramic, oxide ceramic properties. So easy to handle, and sometimes when you dealing with oxide ceramic, of course, this is very difficult if you have a very cost one. It's for clay, it's fine, but this is for fine ceramic, so you need to sintering. Sintering is very depend on the particle size of the material. So why powder? So very simple. Is of course material safe. I show you why safe, and then cost production low. Of course, some machine is very low. Production some depends on the orders, and then we can play with the alloy. You can put many things with the powders, and you can play with it. Okay, so like for example, you can add alumina, zirconia all together. You can see what the properties. You can add with non-oxide, oxide, or you can add metal. So this is powder. So they are very useful. In terms of this composite. Okay, so we're talking about the pressing oxide ceramic. We have a simple pressing. There is a upper punch, lower punch, Okay, lower punch, and the die. Of course, the dies we need to have tungsten carbide, but sometimes for small quantity, of course, you can use hardened steel, all this hardened steel. Because when you push, press, maybe a few tonnage, so you have to eject the sample. When you eject the sample, of course, all this abrasive thing happen here. So it will corrode your die, inside die. So very important to check the compacting pressure. If you compact so high, maybe 10 ton, 20 ton, so you have density, there is a break point where is the graph is flattened. So you don't need to have a compaction pressure so high, otherwise you damage your mold. And then it depends on the application actually. For my case, if acceptable to the application, because ceramic mostly they use for consumable. You don't want to sell your product last forever. Otherwise, you are a business. We're talking about this business. So we have customers also. We mentioned that after this. Why we try to make just enough for consumable. So we maintain our relationship and can supply the parts continuously. Okay, so this is of course, this is crucible. Crucible made by powder press is in attack typing, so it's a continuous process. So of course, this you can sell internationally because it's a very high volume. You can press maybe 1 minute or few sample. So of course, it's a high volume. It's automatic. So I don't know whether this one you can play. So this is example of the pressing. So this is slow. You can do very fast. Okay. So all automatic. So you have filling shoes. You have to eject sample and then push the sample and then put sample. Very production. And this is you can connect it to IR 4.0. So something like that. So this is very very useful. Now the technology is become sophisticated. So we have a lot of controls okay, to play with it and then to make sure the quality is there and the production you can connect to your phone, whatever. You can check the production. And of course, to design the mold, we need some expert from, we cannot do that without a team design the mold because the machine is different and then of course the supply of the machine. So we need to discuss with them how to make mechanism of the mold. For simple parts is okay, but for complicated, we need to have some their ideas. Okay. So once we have the mold, but for similar mold, we can just continue doing the same. I mean, just copy it and then modify it just a bit. But for starting, it is difficult. Okay, so that's why when you're talking about ceramics, it's not only material ceramic, but it's engineering ceramic. Engineering means cover all. It's mechanicals, and of course, you need to make formulation for materials and many things. So production, quality control. This is the whole team of production. And this is recently we make oxide ceramic from alumina. This is ordered by Japanese factory in Malaysia. You see, when you're talking about unit Asia, so we make molds, everything, so we make production. But in here, they just order maybe 10 pieces, 4 pieces, 20 pieces out. So how are you going to make molds? So it's very expensive. This is why you need to find the alternative. Of course, mold costs you maybe 10,000, 50,000 per set. But of course, to produce 10, we don't know whether they are continue supply or not. So we make samples by using other process because CIP, so we machine it. So this is the best way. So we can sell quite cheap to them, and then hopefully they're happy. So we are making it. Maybe in future when this is for start, I think starting. But if they trust it, of course trust, then of course we need to change our production into pressing, unit as a pressing with automatic. But depend on the, like I said, depend on the production or depend on orders. How many parts per month? So this is this is how we think in the company. That's why we try to do production because this thing here happened. So we need to find solution how to entertain the customer and industry. Okay. Our existing production is Gaiping. So I think some of you know already. So this is very challenging because we did this research since in Sirim. So we just trial, and then I was thinking how we going to make production of this because it's quite slow. But luckily there is a way how to make it production, and we did it by SIP, and then we machine by using CNC. But before is using lathe, and of course quite slow, but depend on the price you sell them. Okay, this is different type of what you call it size, M5, M6, M8, M10, M12. So special one. So we have cylinder. So actually, even M6 they have many different dimensions also. So we can afford to make a mold and press it. Because so many more if you want to use it, and then of course you have to change more in the machine, so it takes time. So we try to find out how to make it production and make it possible to supply with minimum cost. So we use SIP and then machine it. The application is really the application. So this is a yellow color, this is a white color. This yellow color is high purity, and this much lower. This is 96%. So we put inside there. There is a spot welding, and this is a nut and a plate. So plate, I'll show you the next slide. Okay, this is Gaiping, the black one. So we have nut, we have plate. So we put plate first into body, and then nut on top of it. And then there is a spot welding upper one with the pressure, air pressure, and then push until all this touch. So the current will go through from here to the leg of the nut, and then to the plate, and then to the lower copper. So this is the main point. The guide pin is acting like an insulator, and the guide is both of them. Okay. So this is the place where the nut and plate stick together. But this is already assembled. The assembled part is in production line in Pro 2, Honda. But actually, when small vendor they make it small part, and then they send to them, and then they, to assembly line they put all together by spot welding also. But you can see the hole there with the nut. This is very important because the alignment must be must be good. Otherwise, there is clearance of the car, so you can see it. So difficult for assembly person in the assembly line to do it. And then this is also, there is a problem when during spot welding process. There is we call it spark, and the particle of the spark will go inside the nut. So during the assembly line, so if that does happen, so they have to stop production. So when you stop production of big assembly lines, so of course cost them a breakdown and then cost money. So that's why they are choosing the best guide pin to avoid it. Okay, so luckily we are not still serving them, so I think we're doing the good job. Okay, for clearance of the particle will go in there to avoid this particle. Okay. Okay, so this is the idea of when you spot welding. I hope you can see. Okay, that is a guide pin, and then you put plate and then nut and then spot weld. You can see that it's what you call it? There is a spark, very hot and spark. And when you spark like that, so there is a particle coming out. This is why I try to avoid the particle and go inside the nut. Okay, this is our machine before using the lathe. Even using the lathe is very limited, and one person, only one lathe. So we make the head of our guide pin. This is the head by using manual. manual only. So of course the body you can lace, everything can lace, but to make the round shape we are using manually. So we need skilled people to do that. And luckily we have a Fraunhofer program from SERIM. So we can do many things. Many things. So we can do spray drying. We can do the CNC machining. Actually, we bought this CNC before the Fraunhofer, but stayed there for 1 year because we don't know how to operate it. Luckily, we have Fraunhofer, then they send the expert, and so we play with the controller. We modify the mold holder, everything. So everything goes fine, and we can make. We try with the wood before, and then everything just doing very nice. And you can see here, it's cutting very nice, and you can do all automatic by using this CNC lathe. Even the round shape. Okay, so and this is requested by customer. So they don't want the round one. So they want the sharp hit. So we do it. Even some customer they want longer one. So it's no problem with CNC. That's why we're thinking that future must be something that we can do with the CNC that they have 5 axis or something like that. So we try to develop something more, not only less, but more on CNC lah. Okay. So what we can do for this one leftover. So normally we can make crucibles and also granite ball, so we can sinter, can use for our process. We can do crucible by sip, or we can do crucible by casting. So you can do many things. So you may say that we are using nearly 100% of our materials. Even if 1% maybe drop to the floor or something like that. Okay, in Fraunhofer also we do have packaging. This for export, but we still have problem with export because we try to export our product to Thailand, Indonesia, but still very difficult to say because in Malaysia also we take longer time, few years until 2 years ago, so we can fully supply to locals. Because when you try to stop their market or their business, someone business, maybe other company business, that is many years ago. Like Proton is starting 1985. So you want to stop their supply, someone else business. They supply a lot of piping from Japan, from Taiwan. So when you can do it, so you try to stop them. So of course very difficult. And you need to do, it's a art how to do it. Okay, even same also in Thailand and Indonesia. So we send sample, we send many things there, but of course the supplier they have a long relationship with eco company, so very difficult. So we just send it to them to try everything. So we hope in future just pray that in future they will have they have problem. We don't pray problem, but hopefully there is a chance for us. If there is problem, so they are seeking for another manufacturer. Okay. So this is our seat. We have one in Mutara Subang and one in Kelantan. So other projects is Rahas. So we just, this is a crucible made by us, by casting. So we put the Rahas and then we burn it. And then we found out we get 10% only of total mass. So it's quite interesting. And we get the Rahas from Sikinchan, Selangor, and we get from Pasir Putih. So if this you can get 10%, so quite many silica. It's not normal silica like sand. This is very fine silica. So you have your natural resources. Why we want to go mining something else? So you have natural, and then you can process it. Okay. this is something that maybe some plant they like paddy field they use silica, they suck silica inside the trunk, everything. But maybe some other plant they suck something from maybe other minerals. So we don't know, because things need to be, of course, research is ongoing, so it's never stopped. And then you need to find out what material plant they have inside. So you don't go mining, everything. So if you have leftover plant, so you can burn and then you can get something for our plant. So it's something you have to try and do it. Hopefully Malaysia is a lot of resource actually. So from silica, so we can turn into silicon nitride, possible oxide ceramic can turn into nitrogen, nitride monoxide. So this is what you say, engineer without tools is like a solid firearms. So me myself, if I don't have the tools, if I don't have the expertise, if the order comes, I said no, I cannot do anything. So sorry, so very sad. Sorry. So this is very important. If you want to do something about ceramics, oxide ceramic, whatever industry, so we need the tools. We need a good knowledge, and we need to try always. So luckily, sometimes when you do research, you find something else which is not related, but can be used for other process. This is happened to us. Then so we keep that, and then hopefully when the time comes, so we can use it. And this guy, of course, when you have everything in your hands, so happy, you can work very happy, big smile. So this is what we want to do. So we want to have something that complete. We have a CNC, we have everything, so we can do many things. Of course, one of the ways we have to do networking for universities and some other research institute, CERIN. So actually, the research and the production is fun, but it's up to us how to to make it a way to make it happen. So if you work alone, of course, difficult. But if you work in networking and in, teamwork, so that's very good. I mean, the future is there. So with hopefully MP M2A, so we try to be based of the networking, and then people. Actually, this is no secret. Actually, for us, actually for me. For making one's material, ceramic oxide and oxide, it's no secret. So you can share all together, no problem, for the sake of the Malaysia. I mean, we don't want the country to be leading of this advanced material. We try not to see Thailand or Vietnam or Indonesia to lead this. Actually, you can do here. So we need something like networking. That is very important. Okay, so hopefully it will happen in future. Okay, and now. So we try to get the computer-aided design machine in future, so we can play with it. We also require what you call ultrasonic machining, laser machining. So we did that with UTEM, laser machining with ceramics, oxide ceramics. So I think I have to wait for the result. So many things it happen. So hopefully we will go to right track, so we can produce more. Okay, this is for example we try to do, but CNC 5-axis. Of course, there is in data there are many 5-axis, but of course they are very expensive. But we try to do it very cheap way, cheap machine, and cheap process, cheap blank, and then you can sell very on competitive price for the dental whatever component. So actually we already finalized our blank, so we're just waiting for CNC to be purchased or to be available, so we can try our blank. So this is what future for us. Okay, I think so we also do research with UKN, Zirconia, okay, and we also have some social events. So we welcome all the students and researchers to our facility, and please use safety for this uh, process. And then thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Baiklah, terima kasih diucapkan kepada Encik Rahimi atas perkongsian sebentar tadi. Sekarang kita buka ruangan untuk sesi soal jawab. Para peserta boleh bertanyakan soalan melalui ruangan chat yang disediakan atau membuka mikrofon untuk bertanya.
Nampaknya dah tak ada. Okay. Okay.
There's one question in the chat box.
Yeah. Yeah.
There's one question.
Arc melting. Okay. Do you have arc melting machine to produce custom made alloy? In Serim, they have induction melting. We supplied before. It can goes to 1008 degrees Celsius and high vacuum. I think you can ask Serim whether the machine is okay or not. I can introduce 2% charge. Okay. So of course alloys is you melting the alloys.
Terima kasih diucapkan kepada para peserta yang mengajukan soalan sebentar tadi. Diharapkan jawapan panel dapat menjawab persoalan para peserta. Seterusnya, majlis diteruskan lagi dengan perkongsian daripada panel kedua iaitu Profesor Madya Nur Aini binti Wahab. Beliau merupakan pensyarah di UiTM dengan pengalaman mengajar lebih daripada 31 tahun. Beliau juga terlibat dalam bidang kajian seperti physical metallurgy, composite materials dan powder metallurgy. Dengan segala hormatnya, majlis menjemput Profesor Madya Nur Aini binti Wahab daripada UiTM untuk berkongsi sedikit sebanyak berkaitan Introduction to Ceramic, Taxonomy, Processing and Application. Dengan segala hormatnya, majlis dipersilakan.
Assalamualaikum. Boleh dengar?
Boleh, Prof. Boleh.
Okay. Assalamualaikum, and very good morning. So thank you for the chairperson, and welcome to all the participants and fellow presenters. So my topic this morning is ceramic, taxonomy, applications and processing. Now, ceramic is originated from a Greek word, keramikos. Ceramicus means burnt stuff. So firing is the common word for all ceramics. If you look at all the items in this slide, not all the items here are ceramics. For example, these are metallic materials. And if you look at the second item, we have a combination of ceramics. These three are ceramics. And this is polymer. So generally, materials can be classified into metal, ceramic, and polymer. Now, do you believe me if I tell you that your life is dominated by ceramic? You started your morning with ceramic, and before that, you are in your brick, cement, and glass home. This is your home, which contains bricks, cement, and glass. And if we take into the bedroom here consists of ceramic tiles. And of course, every morning you woke up by your quartz
Prof,
clock, and
suara
inside
Prof tak apa clear lah.
tak clear.
Kurang kena kuatkan sikit. Maaf Prof.
Okey sekarang. Okey. Boleh dengar ke?
Boleh. Ada kipas kat sebelah ke?
Ada kipas. Ada kipas.
Angin dia agak mengganggu di background dia.
Okey. Kita cuba alihkan. Okay, so sekarang better?
Right.
Kita cuba ya. So every morning you woke up to a quartz clock. So if we pick inside a quartz clock, there is a very tiny quartz here, which regulates the movement of the gears, which control the arms of the clock. Yeah. Now, right after that, you freshen up in a ceramic bathroom. So in the bathroom, we could also see the presence of ceramics, the floor tiles, the wall tiles, and the ceramic sink. And not to forget, the sanitary vest here. I'm sorry, I'm having problem with my slide. I cannot change the slide.
Rasa Prof kena buat macam saya tadi, masa dia kadang dia tak boleh masuk.
Saya keluar dulu.
Kena share tadi macam saya buat tadi, tak boleh nak
Saya Saya tak boleh share slide saya.
Oh, tak keluar juga ya? Mungkin share window, bukan share screen, share window.
Saya share window, tapi
Window tak
button
boleh kan?
share tu saya tak boleh klik.
Oh, okay.
Yang present now tak boleh ke?
Saya
Button present now tak boleh.
sekejap, saya cuba dapatkan bantuan.
Mungkin Aris, kalau ada video boleh itu dulu.
Video.
Ada yang kita punya ni company.
Boleh. Saya share video untuk daripada boleh.
Ada okey tu. Nampak okey tu?
Okey.
Okey. Ada. Kena buat macam tu lah susah.
Tadi dia tak boleh bergerak. Dekat sini tadi, preparing breakfast. Yong, nak pergi dekat meeting? Okey, kita nak tengok video ke kita nak sambung?
Boleh sambung.
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 Okay, now right after freshen up, you will prepare the breakfast in your kitchen. Let us look at surround the kitchen. You have also the floor tiles, the ceramic sink, and if you notice there we have a pottery, ceramic pottery, and of course inside the kitchen there are ceramic containers which are used to store all the spices. And if we peek into the kitchen cabinets, there are pots and dishes, and on top of that, sometimes the pot could be metal or the pot could be ceramic material. Now, your breakfast will be served using pottery cups, and pottery plates. And after the breakfast, I'm very sure that you will sit in front of a computer which is fully packed with ceramic-based electronic components such as microchips, capacitors, and resistors. Before you heading back to your ceramic home, and have dinner using the same pottery, heading back to your bedroom or ceramic bedroom, and again use the quartz clock to be ready for tomorrow. So I can say that we live in a ceramic world. We are surrounded by ceramic. Now let us look at the ceramic chemical point of view. Ceramic generally contains metallic and non-metallic chemical elements, and the properties of ceramics could be classified into three main classifications, namely as mechanical durability, chemical durability, and thermal durability. Ceramics generally have high hardness, high stiffness, and high strength, which means that the brittleness of ceramic is very high. Ceramic could have limited ductility or could has zero ductility. So the problem with this is it may cause problems or difficulties in processing and performance of the ceramic product. In terms of chemical durability, the high chemical durability of ceramics make them resistant to almost all acids, alkalis, and organic solvent. So this is why, most of us style our kitchens, bathroom, and in fact our house with ceramic tiles, which are hard, waterproof, largely resistant to scratches, and they are looking good for years after years. Now, on top of that, due to the chemical bond between present in ceramic material, they have high melting point. And due to the high melting point, ceramics have the ability to withstand high temperature. And therefore, they are normally used as furnace in ceramic industry, furnace lining, and furnace lining for fireplaces and homes, and also in furnaces which are used in refining of metals and heat treatment of metallic materials. In terms of electrical and thermal properties, ceramics are insulative towards the passage of electricity and heat. Depending on the amount of porosities present in ceramics, they could be transparent or translucent or opaque. And for certain ceramics, they could possess a magnetic properties. Now, from the chemical point of view, the bond present in ceramics are mostly ionic, which bind together the chemical elements which are located at the right-hand side of a periodic table, the left-hand side of periodic table, and also the chemical elements which are located at the right-hand side of periodic table. On top of ionically bonded ceramics, you may also find ceramics which are bonded with covalent bond. And diamond is a typical example of ceramic which is bonded with covalent bond. Let us look at the taxonomy of ceramics. Ceramics can be classified into glasses, refractories, cement, clay-based ceramics, abrasive, and advanced ceramics, which are comprising of oxides, carbides, nitrides, and borides. The main content of glasses is silicates. If you look at the table here, which tabulated composition of various glasses, the main content is silicates. But on top of silicates, glasses also may contain calcium oxide, natrium oxide, calcium oxide, and aluminium oxide. Glasses generally are utilized as containers, lenses, window pane, light bulb, and fiberglass, which could be combined with other materials to produce a composite material. Very brief on the shaping technique of glass. Glass could be rolled, or could be allowed to float on a molten tin to produce a glass component. And for a hollow component, the techniques which could be used to form glass is called pressing, or this is pressing. In pressing, we are use gobe. Gobe is molten glass which has sufficient viscoelasticity. Similarly, in press and blow, this is press and blow, we are also using gobe, which has sufficient viscoelasticity to allow the glass to follow the mold contour. And at the right hand side here, you have the fabrication technique which is used to produce fibers. For rolling and floating the glass above the molten tin and also production of glass fibers, we are using glass in the form of liquid, yeah, or it is also known as molten glass. Now, in order to enhance further the properties of glass, glass can be heat treated. The common heat treatment which can be conducted is known as annealing and tempering. Yeah, for annealing heat treatment, the glass is heated for around 15 minutes and allowed to cool slowly in the heating furnace. In tempering heat treatment, yeah, the glass is rapidly cooled. The rapid cooling process will cause the outer layer of the glass component to cool faster compared to the internal part or the core of the glass component. And as a result, yeah, the skin or the outer layer of the glass component is under compression force and the inner part or the center is in tension. So the compression that has been produced will be able to suppress the crack growth, which will consequently enhancing the strength and toughness of the tempered glass. Now, let us look at the application of anneal and tempered glass. As the glass has been heat treated, they are able to withstand a much higher tensile stress and impact stress. Therefore, they are normally utilized in car, yeah, as windshield for the car, for windows and doors for our home, the shelving for refrigerators, glass ovens, yeah, the furnitures, and many other applications where safety is very important. Now, if you look at the figure here, since the glass, the heat-treated glass, will be able to withstand much higher tensile stress and impact stress compared to unheat-treated glass, they will fail, yeah, into this manner. If you look at the windscreen of the car here, the heat-treated glass will not be broken into small and sharp pieces. And the second figure here, if we compare the tempered glass, yeah, the failure of tempered glass and non-tempered glass, you could see clearly that, yeah, in tempered glass, they are the tempered glass are broken into small pieces. But if you look at the untempered glass, the shards here are very sharp. Yeah, look at the sharp edges at the center here. And you can also see the sharp edges in the third figure here. Yeah, so this is how untempered glass fail. Now, if we further laminate anneal glass with a thin sheet of polymer, we are producing laminated glass. Yeah, so if you look at the center figure here, this is a single glass. Yeah, when a bullet hits the glass, as we know, glass is very stiff, yeah, and very hard, has high hardness and high stiffness. Since the energy of this bullet, which travel at a very rapid velocity, is higher than the fracture strength of the glass will shatter. But if we consider a laminated glass, and in this case, yeah, the blue layer here is the glass. The red layer is a polymer material. And in this case, the polymer used is polycarbonate. When the bullet hit the first layer of glass, the glass could be shattered. Yeah, but as the bullet approaching the polycarbonate or the polymer, as we know, polymer is highly elastic. The polymer has the ability to dissipate the energy of moving bullets and consequently slowing the movement of the moving bullets. And if enough energy has been taken from the moving bullet, the bullet will eventually stop from passing through the laminated glass. So here, if you look at the sequence of event that we have when we are using laminated glass is normally used as a bulletproof glass, yeah, in homes or offices or banks and also in vehicles. Now, the second type of ceramic is refractories. Yeah, refractories is a ceramic material which has the ability to withstand high temperature without melting or decomposing. Now, since refractories has good thermal properties, they are normally utilized in application which need thermal insulation. And in order to further improve the properties of refractories, we may add alumina. Yeah, so if we look at the phase diagram of temperature versus the content of alumina added to refractories, we can see that at low alumina content at this point here, this is called eutectic point, which is located at estimately 1587 degrees Celsius. This temperature is not suitable for refractory application, which normally involve a temperature above 16 degrees Celsius. So in order to achieve or to improve the refractory properties, alumina content is further increased. And if you look at alumina content at this point, the temperature is further increased to 1890 degrees Celsius. Yeah, so this is the application temperature as a result of higher alumina content in the refractories. Now, another application of refractories is as power line insulators. And we could also use refractories in a process of metal pouring, as furnace lining. And depending on the oxide and silicate content in the refractories, we may classify the refractories into acidic, basic, and neutral. And most oftenly, refractories are maquetted in the form of bricks. The next type of ceramic material is abrasive. Abrasive ceramic is normally used to wear to grind or to cut other softer materials. If the hardness characteristic is the main requisite, the abrasive used should be diamond. If the wear resistance is very important, then we should go for silicon carbide. If toughness is the main requisite, then we should go for tungsten carbide. And if the refractoriness is very important, then we should go for aluminium oxide. The area for application for abrasive grinding, polishing, cutting, and drilling. They could be utilized as oil drill bits, oil drill bits, as cutting blades, and they could also combine with ceramic material to produce a cutting blade. Another class of ceramic is cement. The main or the unique characteristic of cement is when cement powder is mixed with water, they will form a paste which is able to set and harden. Cement is generally used in concrete for construction area, for roads, and also for producing ornamental products. Now, among the cement, Portland cement is the one used in a large quantity. So in order to produce cement, the raw materials are clay, and on top of clay, we have to use lime-bearing materials such as limestone. Those two are mixed in appropriate proportions, followed by the calcination process, which involve heating of the mixture to a temperature about 1400 degrees Celsius to produce what's so-called clinker. The clinker should be ground, to produce a very fine powder. Gypsum is added to the clinker, and the resulting material here is cement. So cement is basically containing clay, limestone, and gypsum. Now, before we could use cement, the cement powder should be added with water, and addition of water will produce paste. The paste has the ability to set and harden with time. Now, before we have a look into a clay-based ceramic, let us look at very brief on technical or engineering ceramics, which are comprising mainly on oxides, carbide, and nitrides. A typical example of oxide ceramic is alumina. We also have zirconia. Generally, these oxide ceramic have good hardness, low thermal conductivity, and good corrosion resistance. And they are normally utilized as bioceramics, as electrical insulators, as electronic components, and refractory bricks. For carbide, a typical example includes silicon carbide, tungsten carbide, titanium carbide, tantalum carbide, and chromium carbide. These carbide have high hardness and very excellent wear resistance, and they are normally utilized as cutting tools. For nitrides, the common ones are silicon nitrides, boron nitrides, and titanium nitrides. These nitrides are very hard. The high hardness characteristic is associated with high brittleness. They have high melting temperatures, except titanium nitride. And for silicon nitride, they can be utilized as components for gas turbine engines, rocket engines, and as crucible for melting processes. For boron nitride
Prof.
and titanium nitride,
Prof,
they
maaf potong. Diingatkan Prof ada masa lagi 3 minit untuk berucap lah.
berapa minit?
3 minit lagi.
3 minit. Cutting tools, yeah, and coatings. Now, for the clay-based ceramics, yeah, we have structural and white west. The structural clay-based ceramics are normally utilized in application involving stress, and white west are those which pay more emphasis on aesthetic values. These are the components in clay-based ceramics. Yeah, clay is very important in clay-based ceramic because clay has hydroplasticity characteristic, which allow them to be shaped into a final component. And on top of that, clay also is able to handle moisture. It may contain moisture. Yeah, and the third characteristic for clay, it is able to vitrify, yeah, harden and form a dense and strong ceramic component when heated to elevated temperature. Okay, I would like to draw your attention to the evolution of clay-based ceramics. Yeah, this is how clay-based ceramic looks after it has been shaped. It has been dry. Yeah, and this is a clay-based ceramic which has been fired. And this is how the clay-based ceramic looks up after it has been glazed. So glazing could be termed as a finishing operation for a clay-based ceramic. Glaze is applied basically to improve the final appearance and strength of the ceramic component. And they could be applied by dipping the ceramic component into a glaze. This is particularly used for a small ceramic component. Could be spray or could be pour over the ceramic component. And they could be brushed, yeah, or they could be brushed, or they could be painted. If the ceramic component has been glazed, they must be fired to make sure that the glaze apply adhere on the surface of the ceramic component. Yeah, so this is the ceramic component without glaze, and this is the ceramic component which has been glaze fired. Ceramic also could be used, yeah, as biomaterials, particularly in orthopedic and dental applications. But I would like to wrap up my presentation by methods to strengthen ceramic materials. Yeah, in order to produce a strong ceramic material, you must make sure that the raw materials are homogeneous. Yeah, before it can be shaped into a final product. This is what I mean by uniform starting materials. You could also control the firing parameters in order to produce a fine grain ceramic products. Yeah, you could also control the firing parameters to minimize the presence of porosities. You could also introduce compressive surface stresses in the case of glasses by heat treatment processes. Yeah, and you could also improve the properties of ceramics by using fiber reinforcement technique. Now, when you plan to use ceramics and glasses, yeah, you should carefully select the composition of the ceramic material. You must also carefully select the processing methods to shape the raw materials into a final products. Yeah. Similarly, it is also applied to the finishing operations. And the last factor that should be taken into consideration is the assembly method if you were to use ceramic with other materials such as metal and polymer. So that's all for my presentation. Sorry for all the hiccups here. I apologize for all the hiccups. Thank you for listening.
Thank you.
Majlis mengucapkan ribuan terima kasih kepada Profesor Madya Nuraini binti Wahab di atas kesudian menyampaikan perkongsian itu tadi. Sekarang kita buka ruangan untuk sesi soal jawab. Para peserta boleh bertanyakan soalan melalui ruangan chat yang disediakan atau membuka mikrofon untuk bertanya.
Prof, Assalamualaikum. Tanya sikit lah. Di UiTM projek macam ni, macam clay base memang ada So boleh macam mana dia open ke atau macam mana nak cara nak ni?
Di UiTM
Yeah.
memang ada clay base tetapi bukan di engineering. Clay base di art and design.
And design.
Art and
So is it open to public or maybe they have short course or something like that?
Basically those which are available in art and design faculty is more towards aesthetic. Yeah, but I believe they are open for collaboration and I can help you to give proper contact numbers so that you can contact the person in charge.
Okey, terima kasih diucapkan kepada peserta yang mengajukan soalan sebentar tadi. Diharapkan jawapan panel dapat menjawab soalan peserta. Majlis diteruskan lagi dengan perkongsian daripada panel ketiga kita, Profesor IR Dr. Abu Bakar bin Sulong daripada UKM. Bidang penyelidikan semasa beliau termasuklah titanium, metal 3D printing, polymer nano composite for high electrical conductive dan polymer composite. Beliau berjaya mencapai beberapa anugerah seperti Best Educator and Research Award, Top 100 Engineers for International Biographical Cambridge 2011 dan Anugerah Bintara Harapan UKM 2016. Majlis juga ingin mengucapkan tahniah ke atas pencalonan Profesor IR Dr. Abu Bakar Sulong dalam Top Research Scientist Malaysia bagi bidang Advanced Material. Dengan segala hormatnya, majlis mempersilakan Profesor IR Dr. Abu Bakar bin Sulong dengan tajuknya Two Components Macro and Micro Powder Injection Molding of Stainless Steel and Yttria Stabilized Zirconium. Dengan ini, majlis mempersilakan.
Assalamualaikum warahmatullahi wabarakatuh. Boleh dengar suara saya jelas?
Ya, alhamdulillah boleh.
Okey, sebelum tu saya sedang upload the presentation material. Adakah dapat dilihat? Masih lagi sebab dia macam tadilah dia ambil masa juga untuk masuk.
Boleh Prof, dah nampak.
Dah nampak Okey.
Dah
nampak saya pergi kepada reading mode lah. Okay, Assalamualaikum warahmatullahi wabarakatuh. Again, saya Abu Bakar bin Sulong dan izinkan saya membentang dalam bahasa Inggeris. Okay, kami daripada UKM memang biasanya bentang dalam bahasa Malaysia je. Jadi kami minta izin untuk sekiranya untuk membentang dalam bahasa Inggeris. Agak pelik sikit lah. Okay, mungkin pembentangan pertama, pembentangan kedua, begitu juga dengan ucapan yang menyatakan oleh kita punya pengucap pertama pada hari ini, iaitu kita punya guest iaitu dekan bagi dekan dan juga presiden bagi MPM2A. Saya mengucapkan ribuan terima kasih kepada UiTM untuk melaksanakan program ini. Jadi kita telah mendengar bagi the first talk and the second talk related to the what we call ceramic processing, what existing apply currently, what the industry need, what the current industry require, what is conventional. I believe in Malaysia scenario, we are not really that too advanced in the ceramic technology. Most of the dominator come still from the international company, but I do believe Malaysia have expertise like from the UITM members, from the IS technology. The other member also able to promote this technology ceramic to more higher. So even though we also have support, support ecosystem like who we are doing, because we have in the what we call in the KKTM, also in the polytechnic, the course, the diploma in the ceramic processing. They're also in the EdTech. We have EdTech also to are doing. So in terms of ecosystem, we are there. So currently, we need to bring that one from the from the ecosystem, from the education to the industry grade. So in terms of the job scope over there, because a lot of people are talking about the job scope, I believe when I do discuss with the EdTech, there are many people who are hunting for the people who are doing in the ceramic processing or focusing in material processing per se, but there are less people who are interested to put their students in the system, education system. For they say in the EdTech, they little bit promoted lah, because EdTech they have fully funded to our people who are study over there. Then we need to support them to ensure that we can get the ecosystem for their engineering. Okay, I bring little bit today a little bit up where something that I foresee maybe it's not been industrialized maybe in this very short term. I hope the breakthrough will be make mostly engineering breakthrough or in science breakthrough will cover 5 to 10 years, where the from that breakthrough then they will come out very production of the some of the component. So today I would like to talk about two components, macro and micro powder injection molding. I do use a powder injection molding as a main processing, but here we believe the topic for the ceramic. So we believe for bifunctional material between stainless steel and erythria stabilized zirconia. The motivation why we are needed this kind, because in near future we can see most commonly the ceramic per se, we have a very good structure in the hardness. They are very good in the hardness, they're very good in the thermal shock, but they have something of their material properties. We are still lower degree, they are not able to have a ductility. They not can be electromagnetic. They also cannot distribute the electrical conductivity or so on. So that is something in the common near future. There are many people when the people want to have a component, they will have tendency to have bifunctional material. So this scope I want to mention today is about bifunctional material, where still we get the remaining of the ceramic property, but have advantage of metal property can put in here. They can be a metal, they can be a metal ceramic, they can be a metal polymer and so on. But here today I will focusing in the metal ceramic for the this one. So I do acknowledge of two students currently how are doing, Mr. Basir, who will be have PhD soon in this month, and then Dr. Bona, who already graduated currently in Nigeria. Okay, then I do mention just now, let's say example of the micro gear. Currently in Asia region, especially Asia region, we are really boom in the electronic application, because more of the big agglomerated company in terms of Apple's, in terms of electronic company in Asia. So we can see the revolution of component become smaller. So there are a lot of miniature or component required from the macro part to micro part. So they have also the functional material, bifunctional material required. Most of currently we can say that two material currently they do a conventional joining process. We do learn before about the joining, brazing, welding, where we add another material, or without add another material, we use a heat or able to join material. But you can see that processes is what we call is a piece by piece processes. It's talking about the joining or brazing or welding. One portion we are joining one part. So it's not considered mass production process. Do imaging if that process is very one by one. It's really what we call especially it's not a mass production. It's really customized product processes. Do imagine if you want to make a very huge amount, so we need a mass production process where injection molding is compression molding one of the remaining of the injection molding in the process where using a molding, using a mold, so we're able to mesh. So that's imaging we're able to use a conventional injection molding process or compression molding to make it by material component. As example here, a micro gear is talking about the heating element. The left side maybe is heating element for the zirconia or so ceramic where they can make a big withstand or heat more higher, but we need to have some portion where you need have a certain density of metal structure. You can see also the example of this. So that thing that been considered as a so however when we are talking about this one, but a single material also, single ceramic also a lot of they are also have a process say in terms of geometry constraint, in terms of design constraint, in terms of the whatever defect maybe being faced by the industry, by the Mr. Rahimi. But in terms of this one, before go to product, they still have a component, the science between the physics between we can need to mention, because two material properties wise that we know that properties of ceramic, they have a higher melting temperature, they need to higher centering temperature compared to metal. And then we do know that the size of that two geometry is different. Mostly metal is more bigger size, and then the ceramic is more smaller size into the powder shape. And then ceramic mostly not come from the spherical, they always come with the irregular or flake, and metal powder come with irregular. So that is all the thing we make, how the processing go through. The more important thing is about their thermal shrinkage, because in order to make it contact bubble, we need to ensure the surface is being able to join, then thermal shrinkage not able to separate the surface between of it. So the thermal shrinkage of the ceramic is what we call thermal shrinkage is higher compared to the metal, then the shrinkage value for the ceramic is higher compared to the metal. So the between balance in it need to be conducted in the manners to ensure that bifunctional material bandwidth. So we're not able to say that that we can get similar joining as a brazing or welding, because it's only a mechanical compaction. We're talking about the powder injection molding per se. So the main problem is that one. Then as mentioned in this just now. So for this presentation, I will do the objectives as below. Because the processing need to flow, so we want to evaluate the flow ability using radiological properties. And then of course we are in this process, we are doing injection molding. They have some people using a compression molding. They can also we do the injection molding parameters. And then in the injection molding we put the solvent or binder. Definitely we need to remove that one. Of course the third objective, how we debinding and solvent mechanism or debinding, the one and the last one about the sintering of two material. So without that one, before we jump directly to the two shaping, either is a macro in the left hand and micro in the right hand side. So definitely we need to know the single material first. So both of the students do the single material of the zirconia first, or do the single material of the stainless steel first. We know what happened in the single material first for the powder injection molding. Then from that one we method how we want to make in the powder injection molding of two material. So in this case, we are doing in two rows in the left and right hand side. The left hand side, either we put a zirconia, and the right hand side we put a what we call stainless steel. We need to use a similar binder system here. And here we are proposing using PEC binder system with the palm steering as for the composition. We do establish this binder many research before. Then we do see the study radiology in the single material, but in the injection molding, we do believe the method of sequence of injection molding. Limitation of the facility we only have a single barrel of injection molding. In proper manner to do the mass production, we need to have the double barrel injection molding or triple barrel or 4 barrel injection molding. So I think in the world now, let's say the company in Germany, they can have a maximum 5 barrel injection molding. Similarly, they can inject for multiple material in there. But that one is technology for the plastic, not technology for the metal injection molding. For God diameter, we are doing a single barrel but we are using a method we call a sequence method. We inject one material, we break the material to half, and then we inject another second material. So the step is really lengthy compared to the conventional one. But if introduced in industry, definitely they need for the mass production they need 2 barrel injection molding. And then the process of debinding and sintering process, and finally for the patient, both follow the same procedure, but macro and micro. Macro, we're talking about the thickness, the width is considered about 3 millimeter, and then for the micro we consider 1 millimeter. And then for the macro injection molding, so we are doing first time we feed the material, we're talking about we put half a kilo, but 5 micro injection molding is a tabletop injection molding. We are focusing to put in the 50 gram of the component. So this is a process for the macro injection molding. I see some of the Brabender mixer, capillary diameter injection molding, boy injection molding, solvent debinding, thermal debinding, and then high vacuum furnace. Thank you for the Rahimi, because she supports some of the technical content of some of the equipment maintenance. So we do believe this will help us in the gain the know-how. Maybe the new future, this technology can be industrialized. Then for the 2C pin, we not go through the high vacuum furnaces. We only we focusing only go through for the tube furnace, because high vacuum furnaces is require. I mean, of course, the furnaces require a lot of energy compared to tube furnaces. Most industry will require. It's better to use tube furnace and the high vacuum furnace. Then and then steady state is the zirconia is really stable. So we do believe. Tube furnace is appropriate for another step for industrialization steps. Then compared to the materials per se here, in the macro one, in terms of the 70 pH in zirconia, we can say zirconia in the nano size 100 nanometer, in terms of the D50, and then 70 pH between 9 micron. So you can see the range of the size is from nano size to the micron. So they can say that we have what we call mismatch between the where you do packing between all the surface. But we have with the next step of the process, we are able to minimize that mismatch. The mismatch there, but we are able to minimize that properties. In terms of the rheology properties, we are do capillary diameter, because we are doing capillary diameter compared the diameter, because in terms of flowing process, they need to flow the injection molding through the 1 millimeter of die or the gate or die. Then that is a good process, because they have another rheometer, but capillary diameter is good for the flowing processes. We can see most of the both material is a plastic, then follow all the material property, rheology property required for the powder injection molding, especially for the metal injection molding processes. And this for the two for the feedstock for the 2C micron, we are repeated again, even though the material is same, but we are focusing in the higher and lower rate of the feedstock. And then we do also the torque diameter study, where we can see the CPVP being critical powder loading. We can see that appropriate been suggested to to the injection molding critical powder loading processes. So this method I mentioned in the beginning what we call is a sequence injection molding, because we only have a limitation of the machinery. We only have one barrel of machinery. Actually, we also try to be a like MacGyver in our lab, try to fabricate two barrel injection molding. They still have there, but it's not working properly because it's in-house fabricated, but still have need to fine tune how the parameters do in the processes. Then, so this is parameter mentioned. I just mentioned just now we do inject stainless steel and then cut it half, put it gate, and then we inject the zirconia in the remaining part, and then we cut the specimen here. We can see clearly believe that the bottom part is zirconia and the bottom part, the above part is stainless steel. That is different on color. So for injection molding, it's not that much problem or defect we found, but the always problem happen during the thermal debinding or solvent debinding and thermal debinding and sintering process, because during that time you remove the binder, then the surface becomes the cracking, and then when you do the shrinking, because thermal shrinkage is different, they can be separated. So a student two students have a very challenging time to find the very best parameter to able to make it minimize the defect, that one. So this for the green sample. That's for the green sample image of the left hand side is stainless steel, the right hand side is zirconia. Then for the micro one, we can see the evolution over here. We can see where we do the injection molding very low, we are not able to get the complete single material. When we increasing the injection molding temperature, we can get more filling component. So with this one, we're able to combine the parameter, that the parameter we make for the both injection molding parameters. So I mentioned now we inject the stainless steel, and then we cut half, and then we inject the zirconia. But we are not using a similar parameter injection for both material because the sequence is different. So another thing that we want to know, the study we want to do for the remaining of the binder, because even though it's two material, but we are using a similar binder. But as you know, the size is nano size and micro size. So they will be what we call the binder removal is become a very different mechanism. So in this case we are using binder mechanism. They have a lot of error. So at the end, we come up with this one to able to withstand the solvent and thermal debinding method. So some of the defect we found in where we are doing the micro component part during the cracking. You can see the left side is single material or stainless 70 pH. Zirconia, the bottom part, the bottom guard is where we do a combination of both material. So we able to make it at the what we call at the higher temperature of 70 degrees and nearly the 40 minutes. Then solvent debinding, we can see for the cold micron, and then for me we can see the cracking. When the good one we can get S here. Then a lot of the images, bottom part of the microstructure images, how the images of the metal part and ceramic part, there is a big difference of the sizes. You can see the capillary effect will be different. That is very good if somebody want to explore how what we call physics, because how numerical simulation can solve the debinding mechanism between this interlayer of the materials. Then for the thermal debinding, this for the left hand side is for the macro one, the right hand side for the micro one. During that one, we can see there's a large pore being opened up during it. But in this case, we still cannot see the shrinkage because we are not jumped to the sintering rate. But we do believe internally there is a pore there, opening pore for the capillary effect. Then when we do the sintering, a lot of the parameter are done for the capillary sintering. You can see for the left side is a macro one, the right hand side is a micro one. So most for the macro, you can see very significantly shrinkage of there, because the contact area, the surface area, looking for the sintering for the macro one is more bigger compared to the sintering, make it the shrinkage value for the zirconia is bigger. The stainless steel of 70 pH, that one is lesser shrinkage value, and then compared to the ceramic for the macro one. So you can see also the heating element also, the heating rate also very low into that one. Then for the this one we mentioned, the left hand one we make in vacuum furnaces, the right hand one we make it in the tube furnaces. So consider this one, the whole cycle actually, from the beginning of heating until cooling. For the vacuum furnace, they take nearly 2 days, and then for the micro one, they take nearly also 2 days. So even though it's lengthy process, we need, because we try to make it faster, but a lot of cracking will be added. So we need to make very slow to ensure that less thermal cracking between the surfaces. Then again, for the sintering processes, in terms of the what we call temperature, in terms of the theoretical density for the macro, for the left hand side, for the micro, for the right hand side, we can see theoretical density is very close to the 100%. We cannot have 100%, but we are above 90%, where most are recommended by all the powder metallurgy method to get more than 90% of the theoretical relative density. In terms of shrinkage, I mentioned it physically before, we can see also in here, we can see for the both when do the combination, the shrinkage in between the steel 70 pH and then zirconia, so in between. Similar to the micro also, the for the both of the joining material, the shrinkage is between stainless steel and zirconia. So it's follow the theoretical or that we able to predict what happened in that methods. And compared to the hardness properties, so the hardness property little bit between macro and micro. Most if when we are doing the left hand side is zirconia for the macro, the right hand side is stainless steel. So if you can see for the macro one, it's similar when I do become a thesis reviewer for the welding or joining press or brazing one. They are the center point, they got a certain hardness, but they are following the higher to the lower if talking about from zirconia to the stainless steel. But interesting happened for the micro one, the hardness value is somehow it become peak at the joining area, but it's not similar to the zirconia where they can get hardness value of the higher. But in terms of the hardness value for the zirconia using the MIM process is quite higher compared to the macro one. 400 I think is not for the zirconia, is still lower, because most of the hardness value for the casting for normal in material is about, let's say it's about 800 to 600, above that one for the HRV value, but it's more comparable to the MIM processes. And then compared to the strength is quite higher for the macro one, but quite lower compared to the micro one. But in terms of the application wise, as mentioned just now, then we are, if the component require bifunctional material, we have a two both material. So we need to a little bit balance between properties strength and then the functional material that we are getting from this two biomaterial component. Then with that, for me, for conclusion in this topic, we can see both material, even the macro or micro for the 70 PA zirconia. For the rheology, follow all the data in the pseudoplastic behavior fulfill requirement. But in terms of the injection molding, we're able to inject not that much defect, but the most defect come when the defect of problem challenges come from the when we do a thermal debinding and solver debinding, then we are carefully need to do the sintering with a lower heating rate with a more longer time, and to ensure there are no separation in the joining surface, and with the performance by the PhD student, they're able to show that a prototype, show that with the sequence method able to make it a micro for metal ceramic joining, where two different material, two different shrinkability, two different sintering temperature able to join in the center, where they get a certain hardness, certain strength that can be used for the mass production of bifunctional material. I think with that, I stop this one. Thank you for thank you for your listening. Thank you for the new and any question. I really want to share comments, and then with that, thank you very much.
Terima kasih diucapkan kepada panel ketiga kita, Profesor IR Dr. Abu Bakar Sulong atas perkongsian yang menarik sebentar tadi. Hadirin diingatkan agar terus kekal hingga ke akhir majlis untuk mengisi link hadiran yang disediakan di ruangan chat bagi dan sijil. Kita buka ruangan untuk sesi soal jawab. Para peserta boleh bertanyakan soalan melalui ruangan chat yang disediakan atau membuka mikrofon untuk bertanya.
Assalamualaikum.
Assalamualaikum.
Waalaikumsalam.
Pak Dr.
Silakan Dr.
Assalamualaikum Pak Abu.
Ini
Is there any alternative to avoid the process of leaching process instead of to debinding stages and make it as a single stage?
So that is a expertise of Dr. Hussein actually. Dr. Hussein actually expertise in the without the water leaching or solver debinding. They need to use a water-based debinder, but they have a group from the Korea, I think, not Prof. Sajapat, Prof. Lee. They are publishing about the code is without the binding process. They also have patent about that one also, but they are using machine judge a water-based binding process, where we are able to remove it during the first step of the sintering. So with that, they have a room to explore this one, but talking about the surfaces, we don't know, because the contact of this one, because the binder is required to make it the surface contact. Previously we are doing a single material, there are no contact surface, just one plane. So we have a contact surface. So we can try with any of the water-based binder system. They're able to just only water-based is able to contact them, because from this one we are really require PE to make it contact in the surface. So there is a room to try. Maybe when this there's room to establish that process. Dr. Hussein.
Thank you, Prof.
Okay, Assalamualaikum.
Waalaikumsalam.
Okay, what you're doing, maybe you can call it pressureless sintering, because you're using the flow gas, and then there's no force during sintering. Maybe you might try to use after during the sintering, there is force. We call it HIP or hot press, and then some hot pressing.
Yeah.
So you have to find how to do that, because joining is very difficult, because two different materials and different properties are different. So very difficult. I think.
Agree. I mean, because whatever in the PIM, also MIM, if they found any of they still cannot get compact, they go to the CIP, AFP. There is a secondary process that they always conducted. So hope if they find we find the application, then if the in the industry say the joining is still not enough, then that is an additional step we can put up the agree truly agree, Mr. Rahimi, yeah, from the aspect. So somebody raise a hand, Amin Malik.
Ya, ya.
Amin.
Assalamualaikum Prof.
Yeah.
Saya Amin Malik daripada MIGE, Malaysian Industry Government Group for Technology.
Yes.
First and foremost, thank you for the very good presentation, very informative daripada pihak industri dan juga UKM. Soalan yang saya nak tanya ni ialah berkaitan dengan pembangunan industri advanced material di Malaysia lah secara amnya. Jadi kalau kita lihat advanced ceramics, bila kita ada buatkan prioritization among the advanced materials yang available di Malaysia ni, advanced ceramics was being mentioned. Cuma saya nak tahu dari to keep it short, untuk pembangunan industri di dalam negara Malaysia ni, kalau kita lihat dari segi availability of raw material, ownership of IP, capability to manufacture dan juga market. Kalau saya tanya soalan ni, tak semestinya jawab sekarang. Cuma nak tahu kalau in the areas of advanced ceramics, apakah application yang boleh that we can leverage on to develop an industry di Malaysia. That is the question. Kalau saya dengan Musti pun dia akan tanya macam okay, you memang sekarang ni saya setuju. Memang tadi ada yang pembentangan yang mengatakan yang dekat Malaysia ni kita siapa ke yang presenter yang mengatakan more or less is focus on fundamental research. Memang bila kita buat study National Advanced Material Technology Roadmap ni, memang kita banyak fokus kepada TRL 1 kepada 5. Jadi bila macam sekarang ni we want more on 8 to 9 kan, towards commercialization, tapi dia ada 2 different KPI. Tapi benda tu reality yang sedang berlaku. Cuma kita nak tahu kalau kita nak develop industri seramik dekat Malaysia ni, kat mana yang kita patut fokus? Bergantung kepada faktor-faktor yang saya sebut tadi, yang tadi tu lah. Availability of raw material, IP pun kita ada, processing capability pun ada, expertise kita dah ada banyak kat Malaysia. Cuma tentang mana yang kita boleh fokus untuk dijadikan kelebihan kepada rakyat dan juga negara. Itu saja, Prof. Thank you.
Okay. Okay, saya menjawab on behalf ke ada Prof Midi kan kadang. Prof Midi yang sepatutnya menjawab yang ni. Okay, Prof Midi tak ada lagi. Okay, saya menjawab on behalf of the ni lah. We do the society because the society to groom this technology, all the about particulate. They can be a metal, they can be a ceramic. So menjawab that question about the features of the advanced ceramic. Cool. So I do believe that advanced ceramic, we have already have facilities. We have already have the technical. Of course, we do not have manufacturers who are able to produce a raw material. Even though we have a lot of silica, where a lot of people we are processing it. We have a lot of silica, but we do have a technology how to process it to become a component. So for me, for us Malaysia, how to transfer this one to vary from the TRL1, TRL5 until to the industrial need. First, the first need to come from the blueprint or the roadmap of the industry, because just now mentioned that Dr. by the Rahimi do mention, because in the automotive sector per se, where the company is belong to Malaysia, so also they have a lot of the ceramic component been used in that automotive component. So currently they be subcon to the very big conglomerate company. So we need to leverage in their vendors to ensure that we be able to have our own marketplace, that we able to bring our expertise to this one. But talking about this one, there are many types of the ceramic. So I think for the slip casting, conventional casting, that one we already established. But for the very more advanced one, like laser or something like that one, is more we need to go through the process of it to able to believe the consideration for might to make consider a blueprint or something about the environmental you consider with the all the stakeholders. Then it required that policy to make it, because now there are no bridge between that the other one to that one, so that need to have make a bridge of that one. In terms of researchers, I believe in Malaysia, in the university level, USM they have minerals engineering. Most of it, for me, I may say that USM more advanced from the others universities in Malaysia because they have a minerals engineering program, minerals engineering degrees, and then they have masters. I do believe we need to accept that one. So, but they have also researcher in the UiTM, there's more. But in terms of the program bigger, USM is leading because they have a minerals engineering. Of course, we also have institute like CIREM who are doing the promoting and then we do believe also we cannot gone away that at KKTM they also had a program of that one. They also missionaries over there. So in terms of the missionary, we are already there. So believe me or not, they have a job scope, a lot of a job scope over there. So that I think similar. Maybe Rahimi want to add on in terms of industry perspective, because Rahimi go all over the world to promote, not only in Malaysia, go to Thailand to promote that one. I believe the value chain is there, but now is how to convince the industry to take it as a Malaysian product. Is it true or not, Rahimi?
Yes, very difficult. But actually, I would like to add one more thing. Actually, we have big customer in Malaysia. That is dental. They are using ceramics, if you believe it. So they are using zirconia, they are using glass ceramic, they are using silicate. So when I was introduced to USM dental faculty, I quite surprised because the process is similar. It's like injection molding there, and then the machining, many things that happen. So actually the dentist left behind. There is some inside, but we actually left behind. So now we have MOU with USM. So we try to develop something that we can produce, maybe crown, maybe something else made from ceramic, and by using local resources like nanosilica and some other thing. Even though we use imported material, we try to use small percentage only. So we can add on, so we make it strong. So I think that's one of the area that we should look at.
Okay. Thank you, Prof dan juga
terima kasih
Rahimi.
We really appreciate the MIT initiative because MIT is our policy makers, dan we are follow the policy makers when we bridge everything. Thank you.
Yeah. That's the reason sebab memang certain things tu they need a policy push. Tapi yalah, nowadays we need to understand ataupun to know where we are kan.
Ya, betul.
Sebab we are actually in the areas of advanced ceramics ni. There are other candidates as well competing with each other. So like so sekarang ni kita memang we are identifying what are the possible candidates that is worth to so to say to invest in, sebab memang kita sedia maklum kalau advanced material ni dia mengambil macam the conventional way, you want to do research, it may takes more than 10 years. Yes. To have it commercialized. Maybe with new methods it can be reduced to half than that time frame lah. But it's a challenge. That's why we need to understand so that when we put it in the report tu kita nak tahu jugalah kan. We try to be fair to others. But then again it's also tough. Tu yang because ceramics ni pun I'm not sure whether because under E&E we have to look at macam high value lah. Last time silap saya whether there are ceramics when involving sputtering targets, ada dia punya sputtering shield kan. I'm not sure whether that is also made of ceramics as well, but itu macam high value products, high value consumer mana selalunya bergantung kepada import je lah. Memang tak ada buat dekat dalam Malaysia kan. Tapi there are companies yang do cleaning of sputtering targets. I'm not sure whether they need some replacement of that what do you call sputter targets punya apa nama? What do you call it? I can't remember. Macam the ring.
Yes, sputtering. Yeah. Sputtering is very well known because of the engine, ceramic engine. You know, so they use sputtering lah, don't be coating.
Okay. Yeah, maybe this is our first encounter. Nanti maybe I'll get in touch with you guys. Alright.
We will channel the expertise that you are. If you are really focusing in dental, we are channeling into the dental. It's talking about the automotive, we channel to automotive and so on. So I mean in our.
Alright, thank you. Okay, thanks.
Terima kasih diucapkan kepada soalan yang diajukan sebentar tadi. Tanpa melengahkan masa, majlis diteruskan lagi dengan perkongsian daripada panel keempat iaitu Puan Marziah Cik Murad. Beliau merupakan pensyarah di Kolej Pengajian Mechanical Engineering iaitu M. Shah Alam sejak tahun 2011. Penyelidikan beliau tertumpu pada peningkatan dan pembuatan bahan bioaktif terutama dalam bidang ceramic engineering. Beliau telah menerbitkan daripada 20 artikel penyelidikan dan memperoleh hampir RM300,000 Malaysia dana penyelidikan untuk pelbagai projek yang berkaitan dengan pengembangan bioceramik berasaskan kalsium fosfat. Antara karya terbarunya termasuk penggunaan sisa bio kita semula untuk pengeluaran hidroksiapatite berstruktur nanos untuk aplikasi perubatan dan pergigian. Dengan segala hormatnya, majlis mempersilakan Puan Marziah Cik Murad.
Nampak tak? Can you see the slide?
Yes.
Okay, thank you, moderator. Assalamualaikum and good morning to everyone. First of all, I would like to thank the organizer for inviting me as one of the guest speakers in this webinar. I'm Marziah and today I'm going to share my current research work on zinc substituted HA bioceramic, which is developed using naturally derived calcium precursor. Before sharing my research findings, let me first give a brief introduction on what is bioceramic and what is HA, or hydroxyapatite, in case some of you are not familiar with these two terms. Bioceramics are advanced ceramic materials used for repair or replacement of damaged bone or teeth that was caused by aging, fracture or diseases. Bioceramics can be bioinert, bioactive or bioresorbable. No matter what is the type, it must have crucial characteristics such as non-toxic, non-inflammatory, non-immunogenic, biocompatible, and it must have appropriate mechanical properties for specific application. Hydroxyapatite is a bioactive ceramic which falls under calcium phosphate family. It has similar characteristics as natural bone and has the ability to form direct bond with the host bone. Because of these reasons, it is widely used in medical field as bone substitute material. Nowadays, researchers are always looking for alternative ways to reduce costs for HA synthesizing, which may in future reduce the cost for bone replacement treatment. Therefore, preparing HA using calcium from natural sources, especially from bio-waste, has now becoming a preference among many researchers due to its simplicity and cost effectiveness. Some of these bio-waste can be converted into HA directly, while some others are used as calcium precursor in the synthesis process of HA. Synthetic HA is typically very brittle and has low fracture resistance. This tends to limit its capability to be used as bone substitute intended for load-bearing applications. One approach to improve the mechanical and biological properties of HA is by doping it with metallic trace elements that are commonly found in physiological wood, such as zinc. There are a lot of works on zinc HA have been reported, but they were commonly developed using commercial calcium precursors. Even so, most of them focus their studies on chemical and biological properties only, not so much on the mechanical aspects. So in this present study, we aim to develop zinc HA using waste chicken eggshells as calcium source and then evaluate its mechanical properties. Due to its high calcium content and abundant availability, eggshell can be considered as a cheap and easily accessible natural calcium source. Okay, let me explain to you how calcium carbonate from eggshell is converted into calcium oxide. To do this, the waste eggshells were first cleaned thoroughly to remove the residual membrane layer. After that, they were rinsed, dried in air, and then dried in an oven at 60 degrees Celsius for 24 hours. To obtain calcium oxide powder, the dried eggshells were crushed before undergoing calcination at 900 degrees Celsius for 1 hour at a rate of 5 degrees Celsius per minute. If you can see from this study pattern, it is clear that in figure 1, you can see that calcium carbonate from eggshells completely transform into calcium oxide after calcination at 900 degrees Celsius, as reflected by the presence of calcium oxide peak, the three main calcium oxide peaks at 111, 200, and 220 plane. FTIR spectra of the powder in figure 2 also shows characteristic bands inherent to calcium oxide structure, which is indicated by the presence of carbonate and hydroxyl frequency bands. Figure 3 of SEM image shows that the microstructure of calcium oxide powders contains a mixture of irregular shaped particles of various sizes, approximately 0.1 to 0.5 micron. Now I would like to move on to the preparation method of zinc HA powders. In this synthesis process, eggshell derived calcium oxide powders and ammonium dihydrogen phosphate were used as a calcium and phosphorus precursor respectively, while the zinc ion source was zinc nitrate. Each reagent was measured precisely according to calcium to phosphorus ratio of 1.67, which is in accordance to the ratio of stoichiometric HA. After mixing and stirring, the precipitates were aged overnight, vacuum filtered, and washed. After that, they were dried in an oven at 100 degrees Celsius for 24 hours to remove excess water. For the fabrication of dense bodies, approximately 4 grams of the HA and zinc HA powders were pressed into a disc shape at about 90 MPa using a semi-automatic hydraulic uniaxial pressing machine. In this study, consolidation of the powders were carried out at 1200, 1250, and 1300 degrees Celsius for comparison, using conventional pressureless sintering technique under air atmosphere. Other parameters such as heating rate and soaking time were set at a constant of 2 degrees Celsius per minute and 2 hours respectively. Now let us look at the microstructural properties of the synthesized HA and zinc HA powders. Figure 7 shows that the TEM images of both powders contain rod-like shaped nanoscale particles. The size of these particles are approximately 30 to 40 nanometer in length and approximately 4 to 5 nanometer in width. CAP ratio of the sample calculated using EDX analysis indicated that zinc HA has lower ratio of 1.63, suggesting that it is calcium deficient, which is to be expected when zinc substitution has taken place in the HA lattice. BET surface area analysis revealed that zinc HA has higher specific surface area with 127 square meters per gram compared to the undoped sample HA with 100 and 8 square meters per gram. According to previous research, nanocrystalline powders with high specific surface area could act as a great driving force for effective densification during sintering because of their high reactivity. So in general, an increase in sintering temperature would result in a higher degree of densification. However, it is quite challenging to achieve full densification at temperature 1200 degrees Celsius and below, particularly when conventional pressureless sintering method is employed. As shown in figure 8, the microstructures of samples sintered at 1200 degrees Celsius still contain many large pores and have poorly defined grain boundaries. These figures demonstrate that the compacts were unable to reach complete densification at 1200 degrees Celsius, most likely due to weak interaction between particles as well as insufficient temperature and time for grain diffusion. In contrast, densification of the sample at 1250 degrees Celsius significantly improved despite of only 50 degrees Celsius temperature rise. The SEM micrographs visibly show that the grains become coarser and more densely packed, indicating that there was strong interaction between pores and grain boundaries at this temperature. Raising the temperature to 1300 degrees Celsius induce a more progressed densification, which leads to abnormal grain growth. And if you notice, the morphological features of these samples comprise of scattered nanometric particles on the grain surface as well as at the grain boundaries. This is possibly caused by surface oxidation due to cooling from elevated temperature to room temperature, leading to segregation of the sintered ceramics. Segregation of the bulk solid, however, can have a bad impact on the mechanical properties of the final product. Meanwhile, XRD analysis of HA samples after sintering revealed that HA phase remains stable up until 1300 degrees Celsius, while sample containing 5 mole% of zinc showed formation of secondary phase beta tricrasium phosphate or beta TCP. However, previous research indicated that presence of beta TCP phase could increase the strength of HA by approximately 1.3 times. If you look at these graphs, you can see similar increasing trend in terms of grain size, relative density, and hardness of the sample with respect to increasing sintering temperature. However, for fracture toughness, the enhancement can be observed in the sample sintered at 1250 degrees Celsius, but then it declined when the sintering temperature reached 1300 degrees Celsius. At 1250 degrees Celsius, 5% zinc HA was found to have better fracture toughness with 1.55 MPa under meter and weaker hardness of 3.24 GPa compared to HA with only 1.29 MPa under meter and weaker hardness of 4.41 GPa. The density for both samples was approximately 95%, and the average grain size is 1.5 micrometer for 5 zinc HA and 2.2 micrometer for undoped sample. Okay, before I conclude this presentation, I would like to show you this table, which comprises the main finding from this present study to previous studies conducted by other researchers. In view of the evidence that I have presented, I think it is fair to say that the findings from this present work is comparable with the findings from Lala et al. Yeah. who use commercial calcium in the synthesis of zinc HA. It should be noted that they employed a more sophisticated sintering method, which is spark plasma sintering, compared to this present study, which only use conventional sintering technique. To conclude this presentation, I would like to highlight some of the key points from this research. The first one is biogenic derived HA dope with zinc ion can be synthesized from waste eggshell through a reaction between calcium hydroxide, ammonium dihydrogen phosphate, and zinc nitrate. Based on this study, the most ideal or optimal sintering temperature was established at 1250 degrees Celsius. Sintering at this temperature revealed that 5 mole% zinc HA has better fracture toughness than the undoped sample. The improvement of the mechanical properties of 5 mole% zinc HA was likely attributed to the presence of tougher beta TCP phase when zinc ion was incorporated into HA. Improvement. In conclusion, it is feasible to use natural calcium extracted from waste eggshell as starting material in the preparation of zinc substituted HA suitable for biomedical application. So I guess that's all from me. Thank you for listening.
Terima kasih diucapkan kepada panel keempat Puan Marzia Cik Murad atas perkongsian yang menarik sebentar tadi. Kita buka ruangan untuk sesi soal jawab. Para peserta boleh bertanyakan soalan melalui ruangan chat yang disediakan atau membuka mikrofon untuk bertanya.
Boleh saya mulakan satu soalan?
Boleh, Prof.
Okey, soalan ni apa dia? Yang biasalah, bagi saya, biasa kalau industri dia bila dia want to invest dengan satu ni, dia akan bertanya tentang yield lah. Banyak mana yang sebenarnya kita perolehi, adakah kita punya yield tu sama seperti mana yang kita dapat sebelum ni lah. Maksudnya sekarang ni daripada from the eggshell, from the eggshell starting point precursor lah, let's say how many gram you put, then how many gram of the HA that you get. So is it that process able to scale up to ensure we can get more amounts of the hydroxyapatite lah?
Ya, boleh. Sebab waste eggshell ni sangat banyak. Lepas tu kalsium memang kita boleh dapat banyak juga. Lagi banyak lah kan. And dia calcium oxide is main ingredient HA. So kalau guna from waste, bio waste, definitely akan reduce cost of HA.
So let's say you started 1 kilo of the eggshell, how many gram you get?
Okay, memang tak dapat 1 kilo lah kan.
Cannot be I think in future you're able to calculate, so you're able to convince the industry that the process was lah, because we're talking about the yield lah.
Yes, true. Tapi itulah saya tak pergi in depth, tapi sebab bio waste yang situ memang sangat banyak eggshell ni. So kalau kita betul-betul manage this waste, kan, kumpul, sedang kat China je 35 million ton in 2020. Sangat banyak sebab orang memang dia macam main ingredient in food kan, food chain guna confectionery, bakery, so dia banyak. So sekarang ni macam mana nak manage that waste, kita nak dapat dia punya supplies, and tapi pada saya memang sangat reduce cost lah, because calcium oxide commercial is expensive.
Assalamualaikum, boleh tanya sambung sikit is it only for eggshell from chicken or from other things, or from also you can get from bones?
Boleh, bones, bovine, tulang ikan, banyak bio waste, yes. Sebab calcium carbonate content ni tinggi, so kita memang boleh convert lah. Daripada tu siapa nak mengumpul tulang ikan tu payahlah sikit kan. Tapi ada study yang dah buat, and memang boleh. Dia boleh produce HA guna tulang ikan, tulang ayam, tulang lembu.
Is it calcium carbonate similar to ini assembling factory daripada mining itu lain ya?
Tak sama. Sebab dia ada ni iron lain sekali. Dia sebab tu orang prefer untuk guna for biomedical application sebab dia ada traces of iron yang suit dengan kita punya bone.
Okay.
Tapi saya ada nampak tu guna untuk eggshell, diguna untuk mixture dalam cement, tak tahulah. Itu application tu saya baru nampak. Quite new to me tapi saya tak study yang tu. So ada jugalah untuk application non-biomedical.
So biomedical ni normally related to of course medical device lah. Medical device is different thing, but biomedical is maybe because maybe more complicated because you put inside the body. So medical device also inside the body, so a lot of things.
Kena consider banyak kan sebab dia ada clinical, nak kena go through clinical studies.
So much Okay.
Dr. Mazia can do the connection with the Granulab lah, I mean in the serum lah, because
yes,
we have a lot of top-down project to make it a HA something, so maybe that can be something that be interest to them lah, because they already spin-off company over there in Adolsi Appetite.
Okay, boleh saya bertanya?
Ya.
Okay, Indonesia ni gimana untuk didapatkan supply of kulit telur tu?
Boleh apa? Kulit telur?
Yang banyak lah.
Kita tak buy, kita memang ambil waste lah macam daripada food. Macam contoh kedai-kedai kan. Memang banyak guna telur, kita ambil waste daripada dia. Kata kita nak minta telur, dia akan bagi. Free of charge.
Okay, di Indonesia ni ada certain industri yang menggunakan telur as the ingredient lah. So kulit telur tu dia selalunya is as a waste. So basically in order you to make the punya tu dengan volume yang besar lah, if you go to economic scale you kena volume besar. You have to seek this waste from kilang-kilang lah, macam kilang buat mayonis ke, kilang buat bakery ke, and then from there you can get a lot lah. And then the conversion tu seperti yang Dr. bertanya, is a conversion tu you must know the conversion from CaSO3 to CO2. How much lah in order to get the volume. Okay. Selain daripada kulit telur, basically kita juga boleh menggunakan ada biogenic resources, right? Bio-based resources. And basically juga boleh guna coral base, batu karang to make the conversion. Itu is more sustainability lah. Kita boleh grow the coral for the HA. Of course you have to make conversion as well. Daripada itu. Okay.
Okay, thank you.
Puan, ada soalan dekat ruangan chat daripada Dr. Muhammad Hafzan. Soalannya berbunyi, bolehkah seramik digunakan bersama PE untuk membaiki well property untuk kegunaan dalam joint implant?
Boleh kalau dalam kes HA ni selalu guna untuk coating. Sebab dia bioaktif, dia boleh bond kan. Dia with bone, dia akan induce bone formation tu cepat, new tissue. So dia tak guna as the implant per se but as a coating. Coating material. Seramik HA lah, saya tak cakap pasal seramik. Seramik secara general macam alumina, memang dia buat untuk bone lah. Implant kan. Alumina, zirconia. Mungkin Prof. Abu Bakar lah tahu kot. Saya HA more towards coating, dental implant. Kalau dalam joint implant memang as coating lah. Not as the joint implant per se. Adakah saya menjawab soalan?
Cik Amin saya mau soalan. Okay, Cik Amin.
Cik Amin.
Dr. Mazia, saya ada satu soalan. Kalau kita from industri punya perspektif kalau kita bandingkan dari segi kos, walaupun di peringkat research level, perbandingan di antara untuk menghasilkan HA daripada kulit telur ni, perbandingan kos dengan cara konvensional, kita dapatkan material untuk HA ni berapa perbezaan kosnya? Nak tahu. Ada some cost comparison ke? Sebab kalau macam daripada kulit telur tu, kalau kita praktik circular economy, mungkin dia jadi macam apa, PKS pula, mula-mula tak ada harga, lepas tu bila dah tahu orang nak guna buat ni, dia ada harga pula jadi kan. Itu satu hal lah. Tapi ada tak cost comparison? Ya.
Saya tak buatlah cost tu betul ni, tapi generally sebab saya beli kan, saya buat dua-dua. Memang calcium oxide ni sebab saya beli from Merck ataupun Sigma kan, dia punya memang mahal, beratus harga dia untuk
per gram?
200 gram, 500 gram macam tu, tak sampai 1 kilo beratus-ratus.
Berapa ratus? 500 gram? Setengah kilo berapa?
Kalau CAO calcium oxide dalam 100 lebih yang saya dapat, yang murah, kalau murah daripada Merck dalam 500 gram macam tu, 100 atau 200 macam tu. Tapi actual kita dapat waste free kan, and calcium oxide is the kita guna paling banyak amount dia untuk produce HA. So meaning calcium oxide kita kena banyak guna, lagi banyak kita guna memang lagi banyaklah cost kan kalau kita beli yang commercial punya. So ni saya boleh saya ada experience buat
itulah
perbezaan dia banyak.
And then macam Prof tadi, Prof Abu Bakar dia tanya juga tadi yang mengenai macam in terms of one of the advantage one of the challenges, macam dia punya yield tu when it comes to mass production, dia boleh replicate lagi, maknanya dia punya repeatability tu boleh berlaku ke in terms of yield, conversion yield tu lah.
Yes. Lah tu saya kena buat calculation tu, tapi pada saya possible, tak mustahil sebab macam saya kata tadi, waste ni banyak sangat, dia million tons kan, jadi takkan kita tak boleh kan produce banyak calcium oxide di situ. Tapi nak bagi for fact tu tak dapat lah sebab saya tak buat real calculation, but maybe in future I can do that.
Alright, thanks.
Okay, thank you.
Thank you.
Terima kasih diucapkan kepada semua yang mengajukan soalan sebentar tadi. Diharapkan jawapan panel dapat menjawab persoalan para peserta. Seterusnya, marilah sama-sama kita menyaksikan video montaj daripada Precision Research Group UKM yang berfokuskan metal ceramic fabrication, titanium foam fabrication and polymetric composite process. Majlis diteruskan lagi dengan video kedua yang disediakan oleh para pelajar latihan industri di Majlis Saintifik Sdn Berhad. Video yang berkisarkan proses penghasilan penapis air daripada abu sekam padi. Video yang seterusnya disediakan oleh para pelajar latihan industri daripada RS Advanced Technology Sdn Berhad yang bertajuk Process to Produce Ceramic Guide Pins. Semoga video yang dikongsikan sebentar tadi dapat memberikan manfaat serta pertambahan ilmu kepada semua. Kini kita beralih pula kepada panel kelima, Encik Abdul Rahim bin Muhammad Sahab daripada Siring Berhad. Beliau merupakan penyelidik kanan di Pusat Industri dalam bahagian nanoteknologi dan mempunyai pengalaman lebih daripada 20 tahun dalam bidang ceramic material and fabrication. Untuk pengetahuan semua, beliau merupakan lulusan ijazah sarjana muda dalam bidang kejuruteraan mekanikal dan ijazah sarjana dalam bidang sains seramik dan seramik komposit. Dengan segala hormatnya, majlis mempersilakan Encik Abdul Rahim bin Muhammad Sahab untuk menyampaikan perkongsian yang bertajuk Formation of Hollow Shape Ceramic by using a new integrated slip rotary molding technique. Majlis dengan ini mempersilakan.
Oops. Sekejaplah, share dulu. Dah nampak tak?
Nampak.
Nampak.
Okey, terima kasih kepada Miss Chairman dan webinar Ceramic Technology 2021 kerana menjemput saya untuk introduce ataupun menggunakan salah satu proses ceramic teknologi yang sebelum tu saya kenalkan saya Abdul Rahim bin Muhammad Sahab. Saya daripada Siring Berhad. Siring Berhad dulu ada blok 18 adalah dulu grup ceramic teknologi, tapi sekarang kita dah di bawah under nanoteknologi, jadi kita agak kurang sikit lah buat research tentang ceramik. Walau bagaimanapun ceramik still kita buat juga, especially untuk testing, characterization and material analysis lah. So my topic today is actually in ceramic dia ada advanced ceramic and then traditional ceramic. Tapi in here is saya cuba introduce salah satu proses yang kita boleh gunakan dalam traditional ceramic. So dia tajuk dia Formation of Hollow Shape Porcelain by using a new integrated slip rotary molding technique. That mean is currently yang kita guna proses untuk buat traditional, kita guna slip casting, then kita convert dia by using rotary molding technique yang similar as polymer material. So this is the shape of hollow shape product which we produce, yang kita buat. That mean is if we see this here, only that mean kita nampak macam dia close lah. Actually dia ni hollow. This hollow shape product. That mean is this is not a big size of the product, but it's about I think for example like this one, red color is about I think that dalam I think 10 centimeter like that. So we can produce like full shape, half shape, and ball like mark. So these are the hollow shape that which I produce at my lab. Okay, what is the current process and the challenging of this process? Okay, currently in the tableware, in the sanitary ware, for example hand former, they are using slip casting technique. So which
we know that this technique or slip casting technique, this will produce the waste. That means the mold and then slip. That's why the challenging is by using slip casting, the waste will produce. So, and also, if we not proper treatment, disposal of the waste, it will contaminate environment and cause health hazard to human. So, and then of course, mold, if we prepare many more from the plaster of Paris, so they require more space for disposal, because the plaster of Paris is considered waste, so they cannot just dispose like that. So this current in the slip casting process. So this is the traditional process. If we see that we need a mold, and then we have to cast by the slip, and then the mold, and then at the end we have the product in the hollow shape product. So this is the traditional process. So for example, like this is a traditional process in the sanitary ware. So the sanitary ware is very big size. That means we need to prepare the slip is the volume is high, and then of course the mold also very heavy. So if we can introduce by using a slip rotary molding process, so it's very good for the industry. For example, like if you can see the rotary molding on polymer process, for example, make a tank, waste bin, so then they need a mold, very big mold, and then just pour a small amount of the plastic or polymer inside the mold, and then they rotate, then it can produce the product without any waste material. Maybe a bit waste because of the just trim to make sure that the part is in good condition, remove the parting line, for example, or the waste in the excess waste at the mold. So, but just a little bit. So the idea, for example, here, if we can use this for the sanitary ware, it's very good because there is very heavy and very big mold. So the company need to prepare the slip more, and then and also the mold is from slip casting from the plaster of Paris. Then they mean more waste they produce. So this is the innovation which I introduced in the slip casting technique. So I replaced the slip casting by using rotary molding technique to produce the hollow shape ceramic product. The idea is similar to the polymer material. That means we use the two axes for producing hollow shape ceramic product. So this is the key point. The key point in order to produce the hollow shape ceramic product by using the integrated slip rotary molding technique. That means is the important thing we have to produce the slip high solid content. That means is it's not the normal casting. They just about 60 to maybe 60-65%. But here we need to prepare the weight percent of the high solid about 73 and to 80% weight solid in order to produce the hollow shape. And then also this is if we put the slip, the high solid content slip inside the mold, then we have to rotate by two axes to produce the hollow shape product. Of course, they have a parameter like speed, temperature, and time in order to produce a sufficient and quality product. So this is the flow, the picture or the process flow, how to produce the hollow shape by using the rotary molding technique. integrated roti molding. So like I mentioned before, we have to put the high slip inside the mold, and then we had to set the temperature and then rotate the mold at 2 axis, and then after certain time we make we blow the air to cooling the mold before we can remove the product from the mold. This is the concept of the integrated slip roti molding process. So what is the advantage of this technique? Of course, the advantage is we want to replace the traditional technique by using slip casting for cost saving and environment protection. That means here we just prepare the slip. That means we prepare the slip at the amount we needed in the mold, and then we pour inside the mold, and after rotate, no removal of the waste. That means we have to consider the thickness required. For example, in the slip about 3 to 5 mm. Then we have to consider, we have to calculate, and we have to prepare the slip, and then we rotate the slip inside the mold. Then we will produce the hollow shape. So here no waste slip inside the mold. That means we no need remove. For example, if in the traditional process, when we pour the slip inside the mold, after certain time, when the thickness, for example, achieve, for example, 5 millimeter, then we have to remove the waste, the slip inside the mold to get the product. And also here, so we don't need to remove the slip. So it's good for us in order to produce the product. And then also from here, like polymer material, by using a rotary molding technique, we use a mold. Then here similar, there we use a mold from the either porous metal or porous resin instead of plaster of Paris. Why plaster of Paris? The life is only 70 to 100 casting to produce the quality of hollow shape. But here we can stand more because we're using the good material, hard material, in order to produce the mold. And also mold can make by using the CAD/CAM technology. That means we can draw and then CAM by using technology for mold fabrication. These are the potential market of this process. Of course, the hollow shape ceramic, that means is from, for example, from porcelain, stoneware, alumina, we can produce the hollow shape by using rotary molding process. And then, of course, in Malaysia, slip casting is the highest process in the ceramic, especially for producing sanitary ware, tableware, and also can use for the thermal industry. For example, can make it crucible. That means we can cast by using aluminum oxide, and then can produce a thermal industry like a crucible. So any product from ceramic then can produce for using this technique for hollow shape product. So this is the equipment. The equipment is we fabricate by CRM. This is the equipment fabricated by CRM. We do it by ourselves. So then we rotate it inside the mold, then produce the hollow shape. This is the system we fabricate. That means we have 2 axes, and then we have the temperature control, blower for cooling, and then timer. Of course, in order to produce here, we have to modify the slip. We need a coagulant, special coagulant to produce, because this is high solid content. That means is we have to produce the slip is low viscosity to rotate inside the mold, and then we have the binder to give a strong of the body and dispersion. The normal using in the slip casting process. So this is the example product which we produce by using our rotary molding technique. But here this one is the like a mark. So this is the product which we produced after fired, the hollow shape product. So this one is the glaze hollow product. That means after the product fired, we can glaze it, the product for decoration. Okay. This is my conclusion based on the technique. Basically, this technique is one process for replacing a slip casting for producing hollow shape ceramic product. And then the technique is environmental friendly process compared to the slip casting technique, which no waste or possibly eliminate the waste. And then of course here we need a high percent of solid content in order to produce the slip for using this technique. And then of course parameters in terms, we have to consider the parameters of the speed, and then the time, the temperature inside the chamber of the rotary system, and then the cooling time in order to produce the hollow shape product. So here, and then the dispersion we're using here, we're using the polymer based dispersion. And we put binder in order to ensure that the green product is strong in order to remove and then to take the product, or to bring the product, for example, for drying product or green product to the furnace. In this study, I using the porcelain from Japan, and also using aluminum oxide to produce the product. Of course, the solid content, if you can get higher, is better. But here is I can produce about 75% weight percent, which low viscosity to produce the slip using for the rotary molding. Of course, in order here I already mentioned the binder is important to form the high strength green body, and then the coagulant porcelain also important to produce the viscosity of the slip. So this is the video that I would like to show you how the process happened, how the process to produce the hollow shape product by using the slip casting, rotary molding slip casting process. The high solid content slip about 73, 75 like that. So actually this is a project award by Malaysian MOSTI. I get the grant to do the research. So actually we get some award from the ITEC and Malaysian Technology Expo. And then this is our system that we analyze by using our system. We have just introduced a bit about my lab at the block 18 in Syrian. We have SRF, VSRT, UTM, SM, the EDEC for the material analysis, testing and analysis. And also we have the furnace, we have also the emitter and model of rupture test. So that's all my presentation. Thank you.
Majlis mengucapkan jutaan terima kasih kepada Encik Abdul Rahim bin Muhammad Zahab di atas perkongsian yang bermanfaat sebentar tadi. Sekarang kita buka ruangan untuk sesi soal jawab. Para peserta boleh mengajukan soalan melalui ruangan chat yang disediakan atau membuka mikrofon untuk bertanya.
Okay, Cik Rahim, ni Rahim sini boleh tanya sikit Is it possible kalau buat besar ni big?
Itulah. Okay. That's the idea sebenarnya. We have to solve the company lah. Actually for the big small company, where they don't have macam facilities, very good facilities lah. Of course lah, as I mentioned before, kalau for example like sanitary ware like toilet bowl tu ke semua tu, dia more dia besar. So they have to prepare the slip very big lah. Banyak lah. Kalau macam big company, of course they prepare banyak-banyak tu, but it's very big, and then in order to remove the slip access tu pun they need energy to angkat the mold lah. I think it's good lah untuk for the big ni lah. Kalau macam small tu kurang sikit, tapi sebab kita just only can produce by using a small product lah. But not that the system is quite big lah.
Okay. Because we're thinking about making a house. you rotate, and then you make windows in the door and then sintering.
Kalau I think it's certain, yes, I think dia better lah. Pasal kita just prepare slip, for example like kalau dalam sini, for example, pada size kita boleh macam 1/3 daripada ataupun 1/3 ataupun tak sampai 2/2. Then kita boleh slip tu kita tak payah buang lah. Kita prepare, kita just put inside pour inside the mold, then kita rotate, then no need to remove the excess slip.
Okay. Interesting.
And then the potential adalah kita boleh gunakan mold daripada non plaster Paris. But then yalah, I managed to get that one. But then is I think in order to get more ni, kita kalau especially pada big kan, kita kena ada sikit study lagi lah.
Okay. Very interesting because we did see some rotational molding for polymer or composite, but this first time I see for making.
Yeah, the idea is polymer dia heat, dia cair, and then they rotate and then cooling. Similar juga Samit, but the idea kita have to put kita kena put something macam coagulant in order to kita hardkan dia balik.
So interesting because you can make a big bowl for water. So instead of casting, very big casting, so you can rotate, then you can have uniform thickness.
Cuma my study only just tak big product lah, very small. Kalau big product mungkin budget kena lagi besar lah.
Terima kasih ucapkan di atas soalan itu tadi. Harap jawapan panel dapat menjawab persoalan tersebut. Kini kita beralih kepada panel terakhir kita, Profesor Madya Dr. Muhammad Ismail daripada UiTM. Beliau merupakan Profesor Madya di pengajian kejuruteraan mekanikal Kolej Kejuruteraan UiTM Shah Alam. Beliau merupakan lulusan ijazah sarjana muda dan ijazah sarjana dalam bidang kejuruteraan mekanikal dan bahan di Universiti Kebangsaan Malaysia pada 1999 dan 2002. Pada tahun 2001, beliau menjadi pensyarah di UiTM sebelum menyambung PhD pada September 2007 di University of Sheffield. Dr. Hussein kini merupakan Ketua Kumpulan Inisiatif Penyelidikan iaitu Industrial Research Methodology Research Group dan Associate Fellow for Smart Manufacturing Research Institute UiTM. Dengan segala hormatnya, majlis mempersilakan Profesor Madya Dr. Muhammad Hussein Ismail dengan perkongsian beliau yang bertajuk Ceramic Processing Research at UiTM. Majlis dengan segala hormatnya mempersilakan.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh dan sekalian tengah hari. Boleh dengar
Dengar Prof.
Okay. Would you allow me to share the screen? The topic given is ceramic processing research at UiTM. I'm from Muhammad Hussein Ismail. Thanks for the introduction daripada jadi tadi. I've been with UiTM, this is the 20th year, tahun yang ke-20 bersama UiTM, and currently head for the Industrial Metallurgy Research Group, mainly focusing on not only for the metallic material, but we also focus on the other type of the material such as ceramic and also polymers and also composite material. Right, so these are the outline of my presentation, mainly on the ceramic injection molding, CIM. The second one is leveraging UiTM industry collaboration, the case study of ceramic guide pin in collaboration with RS Advanced Technologies Niamhat. And then what are the next project with regard to the ceramic processing, particularly on the 3D printing. So this is the bit about the introduction of IMREC, Industrial Metallurgy Research Group, which already officially formed in 2016. With a vision to be a high-profile research center in metallurgy through frontier research and innovation activities. To establish the mission to establish research and consultation profile through outstanding researchers, product commercialization, and high publicity through high-impact publications. So basically, these are the scope of research activities conducted by our team members, mainly on the processing, but we're also looking at the other aspects on the property structures, and the main is on the characterization at every single process involved. So when we talk about the powder metallurgy, basically ceramic processing very close to the powder metallurgy, which provide a host of advantages over competing metalworking technologies. Why this powder metallurgy is considered as a recognized green technology, because all the you can minimize the waste. Okay, is a cost effectiveness, shape and material flexibility, application versatility, and part-to-part uniformity for improved product quality. So these are the example of the product which is manufactured from the powder metallurgy. This one example of the engine sprocket, which is manufactured by pressing techniques. In Malaysia, there's one company involving the manufacturing of this part, which is the company located in Klang, Dymet, producing this sprocket. So when we talk about powder metallurgy, it basically can be divided into several techniques, okay, from the conventional compaction and sintering, injection molding, cold isostatic press, and hot isostatic press. And now with the advancements of the technology, many of the researchers transfer to the additive manufacturing or 3D printing. So when we talk about powder injection molding, this one already highlighted by Prof. Abu in the presentation on the concept of the powder injection molding. So powder injection molding can be divided into two, depending on the type of the powder that we use. It can be ceramic powders or it can be metal powders. So we use metal powders. If we use, this one is a metal injection molding. If you use ceramic, it is CIM, ceramic injection molding. So basically the concept of the processing are more the same. Okay, we have powders, we have binders. So we need to do a pre-mixing, mixing and pelletizing, and then followed by the injection molding. And then after the injection molding, the sample need to be go through the process of called solvent debinding, thermal debinding, and the final stage of sintering. So the figure left hand side showing shows the example of the part shrinkage as a result of different processing stage involved in the powder injection molding. So in order to understand the powder injection molding, we need to understand some of the important attributes, particularly for the powders and the binders. The first one on the powders need to be spherical shape to ease the flowability of the feedstock, particularly during injection molding. And the second one can provide maximum packing density because the higher the amount of the binder that we use, the greater shrinkage that will be experienced after the sintering process. And the third one exhibits good moldability and lowers the powder binder viscosity. So moldability means that the feedstock or the mixture between the powders and binder should exhibit good flowability. This one can be characterized through rheological analysis. And beside powders, another one aspect is binders. Okay, the binder component. Normally, they comprise of at least 2 binder component which has different functions. So the first function as a backbone and the second function as a primary binders. And these are some of the important attributes for the binders. The first one should give good flowability of feedstock during injection, particularly at the different setting of temperatures and pressure. And it should provide sufficient strength of the molded components, and it should be easily removed. Okay, so there are many types of the binder system that have been used by researchers all around the world. Okay, depending on the powders that they use, and also the uniqueness of the binder system that every researchers involved in it. So these are the how the powders affect significantly to powder performance. For example, size distribution will affect to the flow behavior through rheology, packing density, compactability, sinterability, and also mechanical properties. So those who are doing research in powder metallurgy on particulate material, these are the important aspects. Okay, the first one is size distribution, the powder size, how the powder looks like. Sometimes we can get the powders of 20 micron, 30 micron, but the powders, it can be spherical, rounded, it can be irregular in shape. All of these will affect significantly the flow behavior, particularly during injection molding. And the shape distribution, we can alter, we can modify the flow behavior by modifying the size of the powders. Small powders we can mix with the big size of the powders to modify the flow behavior. Porosity, density, thermal properties, surface areas, and also impurity levels. So for the impurity level, particularly how do we receive the material from the suppliers, particularly those who involved in the metal, the understanding of the chemical composition is very important. Particularly those who involved in titanium injection molding, because I'm also doing a titanium, the level of the impurities need to be controlled significantly because titanium easily oxidized, particularly with oxygen carbon, that forming this kind of secondary phase.
Maaf Prof.
Ya.
Prof ada tukar slide ke?
Tukar slide.
Sebab slide page, front page je.
Oh, alamak. Dah.
Okay.
Kalau ni? Kalau ni okey?
Sekarang okey bro.
Oh, saya punya ni je lah.
Sekarang dekat bawah.
Okay. So these are some of the binder system used in PIM. Some already patented, okay, back in 1981, 1976. For example, which system, the binder system comprised of polypropylene, paraffin, wax, carnauba wax, stearic acid, okay, reverse using the methylcellulose, glycerin, boric acid, water, and Johnson using a polypropylene and 70% of corn oil. And then for the Sheffield, the binder system that used by the researchers mainly this polyethylene glycol and PMA, polymethyl methacrylate. So the one that I used during my PhD works, I use this kind of binders, PEG and PMA, water-soluble binder system, where after the injection molding, the sample are immersed in water at warm temperatures to remove the PEG content, and it followed by debinding and the sintering process. So I would like to emphasize on the binder of palmstyrene. Why palmstyrene? I believe that the palmstyrene have been started by the researchers in Malaysia, particularly from UKM back in 2002. Okay, and then because of these unique properties such as natural local resources, because we are among the biggest manufacturers of the palm oil, so we can have the byproduct of this palm oil, which is a palmstyrene. So these are some of the other characteristics such as biopolymer binders, widely available in Malaysia, environmental friendly because it's a natural source. Sorry. Okay, R&D of palmstyrene binder is PIM. Actually, it was initiated by one of the researchers from Indonesian, Iriani, supervised by Prof. Nohamidi. She found that the optimum fractions of the palmstyrene is not more than 50%. So it is impossible to use palmstyrene as a major fraction in the binder system. In her works, she used gas atomized 316L stainless steel powders. And then followed by the researchers from UITM in collaboration with SRIM, Dr. Istiqomah Subuki. We use palmstyrene as a major fraction and successfully injection mold specimen stainless steel up to 80% of the palmstyrene. And then a recent one, 2017, we tried to use 100% of palmstyrene, and then work successfully with the ceramic powder of HAP using 100% injection molding and 100% of palmstyrene binders. And these are some of the palmstyrene-based binder system used in PIM. Okay, back in so some researchers using titanium and HAP, stainless steel with HAP from the researchers from UKM, and in UITM, a group of researchers for the ceramic materials using yttrium zirconia and also HAP synthesized. So in order to understand the binders, we have to understand the melting behavior of the binder system that we use. So most of the researchers, UKM, UITM, they use these two binder system as the main binder components, the palmstyrene and the polyethylene. So based on the DSC curve here, okay, it shows that the melting point of the palmstyrene is about 55 degrees Celsius and the polyethylene is about 106 degrees Celsius. So this gives some insight on what will be the temperature to be used during the injection molding. If we mix the binder comprised of these two components, so the mixing or the injection molding need to be done at a temperature higher than the melting temperatures of the polyethylene binder, which is around 120 degrees Celsius. And results show that most of the researchers do the injection molding at a temperature of 120 degrees Celsius. This one is research conducted by one of the students. So we synthesize as what have been highlighted by Puan Mazia. We can recycle all this kind of the shell. In this works, it was conducted by Nurul Huda Mat Ali, which is supervised by Dr. Istiqomah Subuki from Chemical Engineering, and also co-supervised by Dr. Teng Wan Dung from SIRIM. Topics of her master is injection molding of synthesized HAP powder from clamshell, and we successfully produce this HAP from the clamshell, from the synthesized, and then we're able to do the injection molding. Okay, so from the waste to weld, producing the HAP, and then do the injection molding using the palmstyrene binders base comprised of 60% and 40% of polyethylene. And these are the techniques that we modify in terms of the binding and sintering. So we perform pre-sintering before finally sintered in high temperatures. So these are the methods that we use in the debinding process, where we apply the concept of wicking, where the alumina and the specimen is embedded in the alumina powders, and then the sample is placed in the furnace for the sintering process. And this figure shows the morphological changes as a result of temperatures from 900 degrees Celsius to 1200 degrees Celsius. Okay, you can see that the morphology shows the pores are interconnected. So the idea is this sintered part can be used for the biomedical application, because to mimic the pore structures for the bones. And then another study is conducted by the students, Siti Nur Azlini Abdul Aziz, which is provided by Dr. Mimi Azlina Abu Bakar. We're thinking that it's possible to use the palmstyrene 100% as a binders, okay, without the backbone. So we use 100% of palmstyrene. So the topics of her masters was effect of single base palmstyrene binder on the properties of HAP scaffold. Normally, in a conventional powder injection molding, you need to have powders, binders, and additive. Additive normally is used to facilitate the molding particularly during injection molding and also during the rheological tests. And the temperatures normally using the conventional binders, since we use either polyethylene or polypropylene, the temperatures was in the range of 160, 150 to 200 degrees Celsius. If we use polyethylene, the temperature is about 130 to 150 degrees Celsius. But when we use a polypropylene as a backbone, we need to increase slightly higher to compensate the flow of the feedstock. By having this one, 100% of pump serine, we can significantly reduce the temperatures of injection molding. Okay, because the melting temperature of the pump serine is 55 degrees Celsius, we perform the injection at the temperature of 70 degrees Celsius, and it works successfully. And then we skip the process of solvent extraction. We skip because it has 100% of pump serine, because we're thinking that when we use 100% of pump serine, when we leach in the heptane, so all the powders, all the pump serine will remove, and then there's no binder that support the powders. So we use alternative approach. Instead of solvent extraction, we use wicking techniques. So we place the sample in the embedded with the aluminum powders, and then put in the furnace, and then we perform the binding and then pre-sintering in order to give the good bonding between the particle before the final sintering is carried out. And then these are the processing stage involved. The HAP powders, the pump serine binders, and these are the mix of the HAP and the pump serine. And these are the characterizations of the powder from the particle size analyzer. It's found that the D50 about 18 to 20 micron. The internal mixture that we use, the particle size about 2.4 micron. The mixing temperatures was 70 degrees Celsius using 100% of pump serine. And these are the formulation that we did for the HAP with 100% of pump serine. And then, so these are the rheology. These are the extruded sample from the machine that we have in UITM. So this is the machine that normally we use to characterize the flow behavior in injection molding. So we can study the viscosity, we can study about the shear stress. There are many things that we can get from this data actually. These are the mold that we use according to the standard for the compression testing. And the rheology was conducted at the temperatures within the melting temperatures of pump serine, about 50 degrees Celsius to 70 degrees Celsius. And this is the green part that we produce from the injection molding. And then these are the machines, debinding and sintering. These are methods of the debinding. Okay, so these are crucible, the brown sample. Okay, these are the the heating cycle. Okay, the maximum of 1000 degrees Celsius. And then this is another works conducted by another student, master student, Mahfuzah Zainuddin, on the U3 stabilized zirconia for dental application, which is co-supervised by Dr. Fuad Hussein Al-Bayati from Faculty of Dentistry. Want to see the potentials of the using the pump serine binder system mixed with the U3 stabilized zirconia. And then before we did the molding, we performed the rheological test. It shows that the flow pattern exhibit pseudo plastic behavior, which is one of the important characteristics for the injection molding. Generally, for the injection molding, the values of the viscosity need to be in the range of 1000 Pascal second, okay, about 10 to 1000 Pascal second. So particularly at the operating temperatures. So these windows show the range of the viscosity at the different powder loading. Shows that all sample exhibit pseudoplastic behavior, which is decreasing in viscosity with increased shear rate. And the next figure showed the some of the sample that produced in this process from the green part to the sintered part. And then this figure shows the morphology, how the interaction. So binder removal, you can see some of the binders of pump serine. and after sintering, still there are some pores observed. And these are some of the mechanical properties using the 100% of palmserine. Some, for example, here on the mechanical properties, on the compressive strength and hardness, we perform the mechanical compression, and also we compare with other works on the ceramic processing. Right. The next slide will be on the actually this project is from the PPRN that we received in 2016 and managed to complete this project in 2018. This project is a collaboration between the RS Advanced Technology, which is Mr. Rahimi, and the Faculty of Mechanical Engineering that time. So now we already merged, become College of Engineering in April 2021. Like in the videos presented by the students, some of the videos of preparations of the guide pin. So these are the guide pin manufactured by the RS Advanced Technology, and these are another the different model, different sizes. Okay, so basically the concept more the same. Okay, all of these are alumina powders, and this is a principle of the ceramic, principle of the guide pin, how it is used in the spot welding mechanism. So this is the guide pin where it is used to support the two component which is being welded. And these are the applications, okay, where it is used in stamping process for the car body parts. So the issues of the guide pin by RST actually some dimension of sample after sintering does not match the required dimension, okay, which is lead to 5% rejection. These are the issues of the companies. Okay, some of the they use the turning process, but the issues is sample broken as a result of the material is too stiff, and then lead to broken of the sample. Okay, and then the proposed solution is incorporate a simple mechanism for final machining, because the part the final dimension we need to remove about 50 to 70 micron a diameter, so that it can match with the required specification. And these are the when we consider its past diameter range, about 93%, and the remaining about 5%, more than 5% diameter out of specification. So in this project, we facilitate in terms of how we can fabricate our simple mechanism to improve the dimensions. So from here, okay, the solutions, these are the machine that existing grinding machine. So we come up with the incorporate with the system, and then these are the grinding of the guide pin using the proposed mechanism. Then beside that, we also perform the some analysis using the facilities available in our lab. For example, here the diameter of guide pin. Okay, we test on the 4 models. Okay, model M6, model M8, M10, and M12. So these are the part before this it is rejected, okay, because it is out of spec. And after grinding process, removing the excessive diameters, so all the samples can be used by the companies for the production. And then these are beside. Yep.
Prof ada lagi masa 5 minit.
Okay, yeah, then nearly. Okay, this one is the surface roughness analysis using the machine that available in UITM, and we did some physical inspection and also SEM to compare between the before grinding and after grinding. Okay, so beside that, we are not only on the collaborating on the try to solve the industrial problem. Okay, these are the most motivating the values that we can get from the collaboration with industry. So leveraging UITM and industry collaboration. From the PPRN project, okay, no more dimensional issues, all rejected part can be reused after grinding. Human capital developments. So these are some of the points from this collaboration. We have signed an MOU in April 2019. Placement for student industrial training. We always almost thanks to RS Advanced and Maju Scientific accepting our student almost every year. So far we have a total of more than 10 LI attachments in 2017. And beside that, we're also offering student for the industrial-based FYP, okay, because the attachment for 2 months is not sufficient enough to to give the students on the overall pictures of the ceramic processing and some characterization. So we offer them a final year project. So far we have four final year projects in 2017, which is co-supervised by the industries. And joint organized workshop, actually we started this workshop in 2019, and also today's seminars is a part of the collaborations. And also joint paper publication. This year we managed to produce one papers with RS Advanced. And last, this international student workshop. So when we have students from international who came for the summer program, so we give experience to the students on the ceramic processing at Maju Scientific. So these are the program that we organized in 2019. Okay, during the seminar we also have a workshop hands-on, so to give better insight to the participant on the processing of the ceramic. Okay, so these are the post PPRN, LI come FIP. Okay, the students from Japan doing the 2 days, 1 or 2 days attachment to get know about the processing of the ceramic back in 2019. So this is my last point on the way forward on in terms of the processing. Ceramic injection molding is not many people really know about this technology, but actually the concept of the ceramic injection molding leading to another new technologies with advancement of technology, which is metal or 3D printing. So basically, when we talk about the metal 3D printing, it's not new, but there's some innovation in terms of the development that we can do, particularly on the materials development. So this figure shows the material that was developed by BASF, producing 100% metal part via industrial standard debinding. So this roll, I bought this roll about 3,000 ringgit Malaysia. The stainless steel is very expensive. So basically, when we look at the process, the most similar with the process of the powder injection molding. The difference is in this 3D printing, we can produce customized part. Injection molding, we need to have mold. If you have two components, you need to have 2 molds. But for this 3D printing, you can design as long as you have CAD data, then we can print. You can print it out. Okay, the post processing almost the same. We need to do debinding and also sintering. These are some of the ceramic components, the ceramic filament that already in the market is very costly, about 3,000 ringgit Malaysia. And so now if you look to the many researchers, they're thinking about the innovation of the 3D printing, future ceramic processing by 3D printing is doable using the concept of from the injection molding, where from the filament that we produce, it comprised of the binders. So this figure showed the conceptual processing involved in the 3D printing from the filament. Okay, so making we have filament, print it out, and then the next process, solvent and extraction, thermal decomposition. These 3 stages are similar with the powder injection molding and ceramic injection molding. Then now, so we can use some conventional. We just change the nozzle of the 3D printers. So this is the project that currently we have in UiTM. So we try to produce the filament of stainless steel. We compare with the conventional commercial stainless steel 316L. Hopefully that we can produce the filament in the future using our binder system. And this is quite new, very interesting. Why I'm saying this is very interesting, because non-filament 3D printing, because one of the issues in producing 3D printing filament is the consistency of the flow, particularly we have powders and the binders. So based on my previous slide, okay, we need to produce the filament. Okay, how can we avoid making the filament? So this is a concept of there's a hopper here, and then the flow with the fixed stock. So these are the things that I believe that in the future, many people will be thinking how to modify this conventional 3D printing, having this hopper and how to control the temperatures and everything here. But this machine is quite new. I just got from one company of 3D printing. So we are also thinking on the process of customized component ceramic. I believe that is doable, and the problem of the filament making filament, homogeneous filament can be minimized significantly. And these are our future works. Ongoing on development of HAP on the composite with PLA composite for 3D printing in biomedical applications. For this year, we managed to get 3 grants from my Tripos Industrial Grant, from the Strategic Research Partnership on the in collaboration with Universitas Indonesia, and recently we got a fundamental research grant scheme, which is led by Dr. Farah Shahida. Actually, Dr. Farah Shahida did PhD in ceramic injection molding, so we can try to think about the new ideas on possibility of 3D printing from the ideas of fixed top that from the inside of the fixed top in ceramic injection molding. Okay, these are probably the features, advanced ceramic. So I believe that many researchers are interested to print ceramic, probably with the low setting temperatures and what will be the next process on the sintering. These are the things that need to be further researched. With that, thank you very much.
Majlis mengucapkan ribuan terima kasih kepada Profesor Madya Dr. Muhammad Husni Ismail di atas kesudian menyampaikan pesan itu tadi. Sekarang kita buka ruangan untuk sesi soal jawab. Para peserta boleh bertanyakan soalan melalui ruangan chat yang disediakan atau membuka mikrofon untuk bertanya.
So, Prof, terima kasih kerana menjadi partner. Actually, closest partner lah, dekat pun. So every time normally we always meet to check whatever teknologi terkini. So also sumbangan student lah, mana kita dapat intern student can help our ni lah research. Hopefully we are welcome others also, because we need to combine, and then of course more hits better than one hit or two hits. Okay. So I guess that's all. Question, of course, we always meet, no problem. So we have question every time. So, okay.
Dr. Hussein, I'd like to ask you, not like ask lah, but something like if you can share lah. I'm very interested about your mention about the 3D printing ceramic. Actually, I would like to know whether at your faculty already doing groundwork with the filament. And then the heat of the baby.
For the groundwork, we already started using the commercial stainless steel FDM. We have done the 3D printing, we have done, and then now we are in the process of debinding and sintering. So we also in the process of producing a filament using machine that available. So actually we have a capillary rheometer that also mimic the making of the filament. But actually there's a when you observe the morphology of the commercial FDM, there is actually on the surface there is about coated material about 50 micron that you observe. So these are something that as a researchers we need to know how the methods of the mixing, and that's why in my presentation I put the 3D printing approach, which is instead of producing filament, we can prepare a feedstock and then straight away transfer to the 3D printer. But there are some modifications that need to be made, particularly on the hopper, particularly on the flow and then the pellet size, because this machine is quite new. Same also for the injection molding. Before it is translated into the metal injection molding, we need to do some modification, particularly the screw barrel. The mold need to be oversized to compensate shrinkage after sintering. So same thing, I believe, for the 3D printing. And I believe that in next 3 to 5 years, there will be other researchers who will be working on this. They are not focusing on the making filament, but from the feedstock that developed from the technology of the injection molding, metal and ceramic, and it can be transferred to the 3D printing using the one that the machine that I showed just now. Because I was told that the machine for that 3D printing is about in the range of 30,000. 30,000. So just imagine for the mold for the injection molding, only for the mold, not only
for the machine. Okay.
So we can do anything. For example, composite between the metal and ceramic. We can do even pre-mixing between different type of the metal powders, and then we can perform sintering using the conventional process of powder metallurgy.
Okay. I will like to add on. I mean, because I've been through a few of the powder metallurgy conferences like PM World conferences all over the world. I believe they have a lot of questions from the auditors, let's say from Europe, from Japan, from other Germany country. They have a question: is it additive manufacturing will replace all the conventional powder metallurgy method and so on? So most of the the keynote speaker or the parallel session speakers, or the industry makers, they mention it's not been replaced, but they are really sharing the what we call the industry substance. So they have a section where additive manufacturing will be advantage. Then they have a section where the business, where the conventional powder metallurgy will success. So looking at that for the Malaysia scenario or our Asian region scenarios, so the business is there. Even it doesn't say that the conventional will gone. There's still a conventional will process, but the new business also come with for the additive manufacturing part. So that is the answer from them because somehow most industry somewhere really skeptical. Is it that everything will be transferred to all the additive manufacturing? The answer is not from them, even though from the reported from all the magazine also. So the share market is still there. Like example, like ours, oil, even though we say it's a renewable energy, but green technology, but still the oil is still there. But they have another section can be replaced. Rather than that, I want to a little bit add the palm stearin, our Malaysian grown palm stearin. I think last 2 years that I've been submitted a few kilos of the palm stearin to the Indomim, because Indomim is the big manufacturer of the meme industry in the world that is stated in Indonesia. So believe or not, I communicate with him. They say everything is in order, but definitely I don't know. Is it they already buy or something from the company in Malaysia or not with that one? So I hope they can generate new industry for the palm stearin, because Malaysian, I think only the researchers from Malaysia do proceed about the palm stearin binder based powder metallurgy. So some additional info from me lah.
Terima kasih diucapkan atas soalan dan perkongsian itu tadi. Seterusnya majlis menjemput Profesor Dr. Nur Hamidi bin Muhammad untuk memberikan ucapan penutup sebelum kita akhiri majlis pada hari ini. Dengan segala hormatnya dipersilakan.
Terima kasih seperti Universiti Majlis. Pertama, saya sekali lagi ingin mengucapkan terima kasih kepada semua pembentang yang telah membentangkan kata kerja pada Cik Raimi, PM Dr. Nuraini, Prof. Abu, Puan Maziah, Cik Abdul Rahim, Muhammad Sahab, Dr. Sirim, dan juga Prof. Madia Dr. Husin yang membentang berkongsi dengan kita tentang kerja-kerja yang telah dibuat sebelum ni. Saya mohon maaf lah, walaupun saya on off, saya dengar sikit-sikit dari perbincangan sebab ada satu lagi program yang saya kena initiate sebab saya at the same time timbalan komandan Sukses UKM tu yang hari ni pakai, kalau tengok tu ada paku sikit baju tu. InsyaAllah saya rasa daripada perkongsian tu I'm quite amazed jugalah dengan perkembangan dan kerja-kerja yang telah dibuat oleh rakan-rakan semua, especially kalau tengok dengan Raimi lah, The Maju Scientific and so on. Saya dengan Raimi ni hubungan tu dah agak lama, daripada memula saya balik dengan PhD, started buat research dalam powder injection molding ni. My first student masa tu Dr. Hussein, Hafiz and so on. Iriani, my first PhD student. So kita dah mula buat kerjasama dengan Rahim, Maju Scientific masa tu. Dan saya boleh tengok aktiviti-aktiviti yang telah dijalankan oleh syarikat Maju Scientific dan RS Teknologi ni. Saya ucapkan tahniah pada Raimi. Sayangnya walaupun dekat, saya rasa saya tak pernah lagi sampai ke kilang di Shah Alam, lebih-lebih lagi di Kelantan lah, insyaAllah. Mungkin satu masa nanti sampailah tu. Walaupun my student saya rasa dah ramai yang dah selalu sampai ke sana bersama dengan Prof. Abu. Kemudian kalau saya sorot balik secara ringkasnya, kalau tengok PM Dr. Naraini tadi, dia mula dengan some basic concept of ceramic dan akhirnya dia menyedarkan kita bahawa sebenarnya dalam kehidupan kita ni, daripada kita buka mata sampailah kita tutup mata, buka mata balik, kehidupan kita ni sebenarnya berkisar kepada sekeliling kita ni kita menggunakan bahan seramik. Kadang-kadang kita tak sedar tu, kita ambil take for granted. Dia menunjukkan sebenarnya market potential ataupun peluang-peluang dalam bidang seramik ni sangat besar lah. Prof. Abu terangkan pasal two component micropim and so on, memang banyak peluang-peluang penggunaan dalam masa hadapan. Saya taklah komen banyak lah sebab ini because kita sama-sama dalam tim membuat untuk ini. Dan saya pun tak sempat dengar habis tadi sebab fokus dengan suksesnya tu tadi. Kemudian Maziah on the hydroxy apatite menggunakan eggshell, menghasilkan HA daripada waste material. Kita nampak ada promising futures kat situ dan boleh dikembangkan lagi dan mungkin boleh dilihat bagaimana untuk scale up dan juga kita untuk pastikan dia sesuai untuk dikomersialkan. Selalunya memang bila dalam research kita ni, bila kita buat lab scale, everything will be nampak perfect, but di industri jangan tengok kalau kita scale up, adakah apa yang kita dapat dalam small scale tu akan dapat dihasilkan juga pada kuantiti yang besar. Syekh Abdul Rahim dan Sirim terangkan pasal formation of hollow ceramic using integrated slip tree molding. Very interesting. Saya tak sempat nak komen banyak sebab bila Rahim present tadi, saya terpaksa tu balik pada program sukses. Tapi at the end of the day saya nampak very interesting research, banyak potential. At the same time saya tengok banyak dapat award daripada exhibition. Hopefully this can be digunakan dalam industri kita lah untuk menghasilkan produk-produk dan sebagainya. Dan akhir sekali PM Dr. Hussein memula dengan menyurut kerja-kerja yang lepas, kajian-kajian lepas dalam bidang PIM, dan akhir sekali membawa kita kepada bidang yang terkini dalam industri ini, iaitu berkaitan dengan 3D printing. Saya memang selalu maklumkan kepada pendidik-pendidik dan rakan-rakan pendidik lah. Kita di KPT bila kita melihat tiap-tiap tahun nak meluluskan grant ni, selalunya saya sebagai ketua projek kadang-kadang kena prepare menjawab pada kementerian. Ada berapa banyak projek-projek yang berkaitan dengan additive manufacturing ni yang kita luluskan dalam sesi ni. Berapa banyak yang mohon, berapa banyak yang lulus. Few years back saya selalu hadapi masalah because saya ingat masa memula kita bagi priority pada 3D printing, ada banyak yang mohon tapi semua kena reject. So saya kena menjawab mengapa kena reject. Tapi bila yang tahun-tahun akhir-akhir ni tak perlu menjawab banyak sebab kita kata banyak dah projek-projek yang kita luluskan yang berkaitan dengan 3D printing or additive manufacturing. Dan hopefully bidang ni kita boleh kembangkan lagi dan akhirnya dari semua yang dibentar ni kita boleh dapatkan manfaat pada semua kita antara kita dan kita boleh saya, pada masa yang sama tadi soalan-soalan saya tengok tu ada keperluan ada peluang untuk kita bekerjasama dengan antara satu sama lain untuk kembangkan lagi bidang ni di Malaysia dan juga dengan peringkat antarabangsa. Saya tak nak ambil masa yang lama, saya tengok ramai yang dah mula keluar tadi. Kita daripada hampir 80 sekarang dah tinggal 52 partisipan, dah pukul 1 lebih ni. Ramai yang dah tak sabar-sabar nak launch and so on. Saya sekali lagi ucapkan terima kasih kepada Barisan Pembentang kerana dapat berkongsi dengan kita semua di sini. Saya ucapkan terima kasih kepada urus dia, Dato' Hussein dan rakan-rakan di UiTM kerana mengadakan webinar ini dengan jayanya dan kita harap insyaAllah kita dapat bertemu lagi di occasion yang lain dan seminar yang lain. Saya tak tahu lepas ni di mana kita nak buat. Sebelum kita tunggu yang main seminar, Dato' Hussein dengan Tabu main seminar yang kita rancang nak buat. Memang kita rancang insyaAllah, kalau kita tak rancang memang kita jadi terus. InsyaAllah kita target kalau kita dapat tahun depan, kemungkinan untuk akhir tahun depan supaya kita dapat berjumpa mengadakan seminar tu secara face to face, dia lebih mesra lah sebenarnya. Dah lama tak jumpa. Tapi pada masa yang sama tadi kita dalam grup PM2A tu ada juga borak-borak. Mungkin selepas ni kita nak minta Prof Rijal. Saya tak pasti Prof Rijal ada lagi dalam grup ni atau tidak. Prof Rijal daripada UTM untuk organize next seminar. Kemungkinan berkaitan dengan automation dalam proses dan sebagainya. Sebab itu antara tool yang selalu kita guna dalam bila kita buat research. So insyaAllah saya harap kita dapat jumpa lagi di lain kali di dalam event-event yang lain yang kita akan anjurkan. Dan kita doakanlah pandemik ni akan berakhir dengan segera dan akhirnya kita dapat hidup dalam keadaan sedia kala seperti biasa insyaAllah. So again, saya ucapkan terima kasih kepada semua, terima kasih kepada peserta yang sanggup menunggu sehingga ke akhir seminar. Apa lagi? Well, all the best pada semua insyaAllah. Stay safe, kita jaga kita. Dan itu saya sudahi dengan wabillahi taufiq wa hidayah. Assalamualaikum warahmatullahi taala wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Terima kasih semua.
Terima kasih diucapkan kepada Profesor Dr. Nur Hamidi bin Muhammad di atas ucapan itu tadi.
Okey. Okey. Itu saja. Boleh.
InsyaAllah ni lepas
jumpa lagi insyaAllah. Boleh jumpa lagi, tak ada masalah. Kita selalu ada sini. Tak lagi OC pun.
Wan Zuhairi, Wan Syahruzi tak nampak muka pun.
Oh, Wan Syahruzi pun ada.
Ada.
Nampak lah dia ada Rijal tadi.
Rijal ada dia keluar dah.
InsyaAllah next webinar on the Taguchi organisation.
Okay.
Wan Syahruzi ke nak buat on additive manufacturing?
Wan Syahruzi yang boleh.
Ya, Wan Syahruzi banyak buat research on additive manufacturing. Wan Syahruzi. InsyaAllah kita cuba uruskanlah. Okey, sebab saya pun lepas ni nak share another tu dekat kementerian.
Okey,
terima kasih semua. Okey,
Assalamualaikum. Assalamualaikum warahmatullahi wabarakatuh.
Terima kasih semua.
Right, alhamdulillah. Team, thank you very much for your kind cooperation. Alhamdulillah.
Alhamdulillah.
Like a big applause to all of you.
Okay, thank you.
It's a very good good exposure for you. Arranging the webinar from daripada A to Z kan. So nanti kalau kata next time you want to organize, you dah ada dah cara dia. You already learn. So this is a part of besides your industrial training, you learn something. This one is good opportunity. I think tak ada lagi TLI yang buat webinar. You are the first. Okay, daripada buat buat create email and then sampailah inilah there's the one cycle of the event. So sekarang ni kita dapat feedback lah the form kita dah berikan tu. Cumanya need to follow up with the participant. Ada sometimes participant dia tak tengok. Tapi kalau kata dia nak a certificate tu dia akan isi untuk form tu. Right. Cik Aimi, ada apa kata-kata ni sebelum kita ni? Ni semua yang tim Kelantan dan juga tim ni. Mungkin kita ambil group foto for the committee je. Tadi group foto semua, ni group foto committee pula. Cik Aimi dah live ke?
Rasanya tak ada dah.
Tak ada dah live dah.
Kita ambil foto sikit.
Yang lain tu kalah tim Subang
dia open kamera
dengan tim Kadok.
Tiga. Dua, tiga. Okey.
Okey, jangan lupa masukkan dalam email CV tu. Dalam CV. Sebagai community for the webinars. Right. Terima kasih semua.
Okey, terima kasih Prof.
Okey, jumpa kalau ada rezeki kita jumpa insya-Allah.
Ya.
Right. Okey, jumpa lagi insya-Allah. Assalamualaikum.
Terima kasih Prof.
Ciao.